Right now, one of the biggest stars visible in the night sky is doing something that has turned entire astronomy departments into around-the-clock monitoring operations, and the scientific community has quietly reclassified it as one of the most important objects in the observable universe. This is the story of Betelgeuse, a star so enormous that if it replaced our Sun, Earth would be sitting somewhere inside it, and why what's been happening to it over the last several years has fundamentally changed what scientists thought they knew about how giant stars behave and die. Before we dive in, if mind-bending cosmic rabbit holes are your thing, hit the like and subscribe button. It takes 2 seconds, but it's what keeps this channel alive and the content coming. Now settle in, because things are about to get interesting. On a clear winter night, if you step outside and look up toward the constellation Orion, you'll find it almost immediately. There, sitting at the star's right shoulder position, glowing a distinct, warm, reddish-orange color, unlike nearly anything else in the sky, is Betelgeuse. It has been there every winter for as long as human beings have been looking up at the sky and wondering what those lights were. Ancient Arabic astronomers gave it its name, a term that has been translated and retranslated over centuries, but is generally understood to reference the shoulder or armpit of the great figure the constellation represents. The name itself is a small artifact of how long people have been staring at this particular point of light and feeling that it somehow matters. For most of recorded history, Betelgeuse was simply part of the familiar winter sky. Beautiful, bright, unmistakably red-orange against the darker field of bluer stars around it, but ultimately just another fixed point in a sky full of fixed points. What nobody looking up from the ground for those thousands of years understood was what they were actually seeing. They were looking at a star so absurdly, almost incomprehensibly massive, that the entire concept of scale breaks down when you try to put it into numbers a human brain can actually process. Let's try anyway, because sitting with those numbers is worth the effort. Our Sun, the star at the center of our solar system, the thing that makes life on this planet possible, the massive, blazing ball of nuclear fire that is 109 times wider than the Earth our Sun is, by the standards of Betelgeuse, small, not slightly small, not notably small, tiny. Betelgeuse's radius falls somewhere between 700 and 1,000 times the radius of our Sun, depending on which study you're looking at and how you define the star's outer boundary, since its diffuse outer layers make the precise edge difficult to measure. But even at the lower end of that range, you're looking at a star so large that if you placed it at the center of our solar system, its outer edge would reach at least to the orbit of Jupiter, the 5th planet. The gas giant, the one roughly 483 million miles from the Sun-Earth's orbit, at 93 million miles out, would be somewhere deep inside the star's body. Mars would be inside. The asteroid belt would be inside. You'd have to travel out nearly to Jupiter's orbital path before you'd finally emerge from the star's surface. That's not a metaphor or an approximation for dramatic effect. That is the actual geometry of the situation. Betelgeuse is a red supergiant, a classification that sounds impressive in a generic way until you actually sit with what it means. And even then, the label undersells it. Consider the star's luminosity, the total amount of energy it pours into the universe, which runs to approximately 100,000 times that of our Sunday. Our Sun, already so bright that looking directly at it for even a second causes retinal damage, is radiating an output that is 100,000th of what Betelgeuse produces. The surface temperature of Betelgeuse sits at around 3,500 Kelvin, which sounds cooler than the Sun's approximately 5,778 Kelvin surface temperature, and technically it is, which is why it appears red-orange rather than yellow-white. But lower surface temperature on a star, this enormous, still amounts to an almost unimaginable total energy output, because the surface area radiating that heat is so staggeringly vast. Multiply a somewhat lower temperature by an almost incomprehensibly large surface area, and the result is a star that outshines our Sun by a factor of 100,000. The universe's arithmetic is relentless. The star is approximately 8 to 8.5 million years old young, compared to our Sun's 4.6 billion years. But massive stars burn through their fuel at a ferocious rate, and age in stellar terms depends on the star's mass, not just the number of years that have passed. Betelgeuse has essentially lived the equivalent of a very fast, very bright, very intense life. The kind of life where the biological analogy would be a creature that grows to enormous size, burns energy at a tremendous rate, and dies far sooner than a smaller, more conservative creature would, its compressed lifetime all the more dramatic for its brevity. The star's mass falls somewhere between 10 and 20 times the mass of our Sun, though pinning down exact numbers for Betelgeuse has been one of the persistent frustrations of the scientific community, for reasons that will become clear as we go. The star sits approximately 700 light-years from Earth, though even that number has been debated, with earlier measurements from the Hipparcos satellite putting it closer to 430 light-years, and more recent studies settling on something closer to 700, with some studies suggesting intermediate values around 548 light-years. The distance question matters more than it might seem, because the farther away the star actually is, the more luminous it must truly be to appear as bright as it does from Earth, and all of those calculations ripple through every other physical measurement astronomers try to make. Distance in astronomy is not a trivial measurement, it is foundational. Get the distance wrong, and everything derived from it, luminosity, radius, mass estimates, evolutionary stage assessments, gets pulled out of calibration. What the distance means in a different, starker way is this. The light currently reaching your eyes when you look at Betelgeuse left the star approximately 700 years ago. You are not seeing Betelgeuse as it is right now. You are seeing it as it was in the 13th or 14th century, roughly around the time of the Black Death in Europe, or the height of the Mongol Empire, or the reign of Kublai Khan. Whatever Betelgeuse is doing at this precise moment in 2025, you won't know about it for another several centuries. The universe operates on timescales that do not accommodate human impatience, and there is something genuinely vertiginous about sitting with that fact that the light arriving at your retina right now began its journey before the European Renaissance, before the printing press, before the Americas were known to European cartographers. It traveled across 700 light-years of vacuum to reach you at this moment, and the star it came from may be completely different now from what the light currently shows you. For a long time, astronomers observed Betelgeuse primarily as what it is, a variable star. Not every star in the sky is a constant, steady light source. Many stars fluctuate in brightness, sometimes in highly regular cycles, sometimes in more complex patterns. Betelgeuse is what's called a semi-regular variable, meaning it has identifiable rhythmic cycles of brightening and dimming, but those cycles aren't perfectly clock-like. Two cycles were well established through decades of patient observation, a shorter cycle of approximately 400 days and a longer cycle of approximately 5.9 years. These rhythms arise from the star's internal pulsations, essentially, the star breathing in and out on enormous scales, its outer layers expanding and contracting, its brightness rising and falling in rough synchrony with those physical movements. Understanding why a star pulsates requires understanding something fundamental about the balance of forces at work inside any star. A star is, at its most basic, an ongoing contest between gravity and pressure. Gravity is always trying to collapse the star inward. It never stops, never rests, never relents. The outward pressure, generated by the nuclear fusion reactions in the core, and the gas pressure from the enormous temperatures throughout the star's interior, pushes back against gravity. In a stable star, these forces are in equilibrium, a balance so precise and sustained that the Sun has maintained it for 4.6 billion years without collapsing or exploding. In a star like Betelgeuse, that equilibrium is dynamically maintained rather than statically maintained. The outer layers of the star periodically compress, heating the gas within them, which increases the pressure and pushes the layers back out, which causes them to expand and cool slightly, which reduces the pressure, which allows gravity to pull them back in, and the cycle repeats. This is the pulsation. It's not random variability. It's driven by the physics of how energy moves through the star's enormous, turbulent body. The 400 day and 5-9-year cycles represent different scales of this process, operating simultaneously in the same enormous stellar body like two clocks running at different speeds inside the same machine. Astronomers like Edward Guinan at Villanova University built careers around tracking these variations, feeding measurements into the American Association of Variable Star Observers, a remarkable organization that allows professional and amateur astronomers alike to contribute to the long-term brightness records of variable stars. Because of this collective, sustained effort, the scientific community had a detailed historical record of what normal Betelgeuse variability looked like. Normal variation meant the star's brightness could change noticeably over weeks and months, but within a predictable envelope, oscillating between familiar bounds like a pendulum whose arc you know by heart. What happened, starting in the fall of 2019, was not within any predictable envelope. Betelgeuse has a history that extends far beyond the modern era of professional astronomy, and that longer history is worth understanding because it contextualizes just how unprecedented the events of 2019 and 2020 were. Human beings have been recording their observations of this star for thousands of years. The Arabic astronomers of the medieval Islamic Golden Age, who laid much of the groundwork for the star names we still use today, catalogued Betelgeuse carefully. The Greek and Roman astronomical traditions before them noted it. Ptolemy's Almagest, the foundational astronomical text of the ancient world, compiled in the 2nd century CE, listed Betelgeuse among the most notable stars in the sky and noted its reddish color, a description accurate enough that it's clearly the same star we're talking about, nearly 2,000 years later. That continuity of observation is itself remarkable. Across the full span of recorded human history, Betelgeuse has been there, burning in the shoulder of Orion, one of the most recognizable constellation figures in the winter sky of the Northern Hemisphere. Different cultures gave it different names and embedded it in different mythological frameworks. The constellation Orion has analogues in Sumerian, Egyptian, Greek, Roman, Arabic, Chinese, Japanese, Mesoamerican, and indigenous astronomical traditions around the world, though the specific star names vary enormously. But through all of that cultural variation, the star itself persisted, and its characteristic reddish-orange color made it one of the most immediately recognizable celestial objects to the naked eye. In 1920 and 1921, Betelgeuse became the site of a landmark moment in the history of stellar physics. Albert Michelson, one of the greatest experimental physicists in American history, the man who had earlier demonstrated that the speed of light was constant in all directions, a result that helped lay the groundwork for Einstein's theory of special relativity, turned his attention to the problem of measuring the angular diameter of stars. Stars are so distant that even through the most powerful telescopes of the early 20th century, they appeared as perfect, dimensionless points of light. The technology of the time couldn't resolve the actual disk of any star. But Michelson, working with Francis Pease at the Mount Wilson Observatory in California, devised an interferometric technique, a method of combining light from different points on a telescope mirror to measure the angle subtended by a distant object that was, in principle, capable of measuring the apparent size of a star. They chose Betelgeuse as their target because it was, even by rough estimates, one of the stars most likely to have a large enough angular diameter to be detectable by their technique, and they succeeded. In 1920, Michelson and Pease made the first direct measurement of the angular diameter of any star other than the Sun, determining that Betelgeuse subtended an angle of approximately 0.047 arcseconds in the sky, a number so small it almost defies mental imagery, less than 1/10,000th of a degree, the apparent size of a marble viewed from a distance of about 5 miles. From that angular size and their estimate of the star's distance, they derived a radius of hundreds of millions of miles. Betelgeuse had been known to be a large star, but the Michelson-Pease measurement made its true scale concrete for the first time. Then, in 1996, Betelgeuse claimed another astronomical first. The Hubble Space Telescope, orbiting above Earth's atmosphere and capable of optical resolution far beyond what any ground-based telescope could achieve at the time, resolved the disk of Betelgeuse in direct imaging, not through interferometry but through straightforward photography. The resulting image showed Betelgeuse not as a point of light but as an actual disk, albeit a tiny and somewhat blurry one, making it the first star other than the Sun to be directly imaged in this way. The image showed what appeared to be a large, bright region, possibly a massive convective feature on the star's surface, providing the first glimpse of what the face of a red supergiant actually looks like. These two milestones, Michelson and Pease's 1,920 interferometric diameter measurement and Hubble's 1,996 direct imaging, established Betelgeuse as a uniquely accessible laboratory for stellar physics, close enough to study in detail that other red supergiants simply don't allow, large enough that surface features can be resolved with sufficient technology, and with a documented history of variability stretching back decades. When everything changed in 2019, the scientific community wasn't walking in blind. They had over a century of accumulated data to contextualize what they were seeing. October 2019. To most people, this was just another autumn month. The news cycle was churning through its usual chaos. Most people's attention was directed at the very human-scale events happening on the surface of a small planet. But to the community of astronomers watching Betelgeuse, October 2019 was the moment the measurements started looking wrong. Not wrong in the way a malfunctioning instrument looks wrong, wrong in the way a patient's vital signs look wrong. The star was getting dimmer. Not in the ordinary way it periodically dims as part of its pulsation cycles, dimmer in a way that was deeper and faster than anything in the observational record. Through November and into December, the dimming accelerated. The astronomical community started sharing observations and comparisons, comparing the current data against the historical record, trying to find any previous episode that resembled what they were seeing. They didn't find one. The rate of dimming, the depth of dimming, the particular timing in relation to the known pulsation cycles, none of it fit the template of normal Betelgeuse variability. By the time the world crossed into January 2020, the alarm was real. The star, that had always been one of the 10 or so brightest in the night sky, was fading in a way that had never been documented before in the centuries of human observation that had been accumulated. By the time the dimming reached its lowest point, around February 2020, Betelgeuse had fallen to roughly 40% of its normal brightness, a drop of approximately 2.5 magnitudes on the astronomical scale, where each unit of magnitude represents a brightness change of about 2.5 times. The star that had reliably ranked in the top 10 brightest dropped to around the 25th brightest. To experienced skywatchers who had known Betelgeuse their entire lives as that unmistakable blazing orange point in Orion's shoulder, the change was genuinely disorienting. Even to the naked eye, something was visibly wrong. This was no longer the familiar Betelgeuse. Something had happened, and the question that every astronomer paying attention was asking in labs at Harvard, in telescope control rooms in Chile, in offices at ESO in Germany, in university departments from Tokyo to London, was the same question. What? The phrase that started appearing in headlines, "Is Betelgeuse about to explode?" sounds like sensationalism in retrospect, but at the time, it wasn't entirely unjustified. Massive stars do not dim like this for arbitrary reasons. When a star of Betelgeuse's type and age shows sudden, dramatic changes in brightness, one of the possibilities that has to be seriously considered is that the star is entering its final stages before core collapse. The scientific community, which normally operates with a studied kind of cautious neutrality around dramatic possibilities, found itself genuinely entertaining the idea that they might be watching one of the most dramatic events in the history of astronomy unfold in real time. Papers were being written, telescope time was being reallocated. Emails were being sent with subject lines that, in the usually dry and careful language of professional science, were notably urgent in their phrasing. At the European Southern Observatory in Chile, astronomers were doing something remarkable. They were not just measuring Betelgeuse's brightness, they were actually imaging its visible surface, a feat that is only possible for a handful of stars, because stars are so distant that they appear as perfect, dimensionless points of light through most instruments. Betelgeuse is large enough and close enough that certain telescope systems, specifically the Very Large Telescope at ESO, equipped with specialized adaptive optics and imaging instruments, can resolve the disk of the star itself, can actually see its face. And what those images showed during the Great Dimming, as this period would come to be called, was something that had never been captured in astronomical history. The star's southern hemisphere was dramatically darker than its northern hemisphere. Not uniformly dimmer across the whole disk. As you might expect, if the star were simply cooling evenly, one side was disproportionately dark, giving Betelgeuse an asymmetric, almost wounded appearance in those images. Researcher Miguel Montarguez and colleagues published these observations, and the images immediately became some of the most widely circulated astronomical photographs of the year. They showed a star that was visibly, obviously not behaving normally, a point of yellow-orange light squashed down into a lopsided shape with one hemisphere ghostly and dim. Even to a non-specialist's eye, the images carried something unsettling about them. Stars are supposed to look like points of light. They are supposed to be symmetric, distant, unchanging. These images showed something organic seeming and asymmetric, a stellar object with a visible wound, and that visual wrongness communicated itself even to people who had no particular background in astronomy. Meanwhile, another instrument was providing a crucial piece of the puzzle: the Hubble Space Telescope, operating in ultraviolet light, a wavelength that ground-based telescopes largely cannot observe because Earth's atmosphere absorbs. It had actually caught something unusual happening at Betelgeuse months before the visible dimming began. In early 2019, Hubble detected dense, hot gas moving outward from the star's surface at roughly 200,000 miles per hour. That's approximately 320,000 kilometers per hour, fast enough to cross the distance between Earth and the Moon in less than 2 hours. At the time this observation was made, it didn't trigger immediate alarm bells because Betelgeuse regularly loses material through its stellar wind. But looking back at those observations once the Great Dimming was underway, astronomers recognized that the Hubble data had captured the earliest phase of something far larger and more violent than a routine mass loss episode. Simultaneously, NASA's Stereo spacecraft, a mission primarily designed to track solar weather, positioned in an orbit that gave it a different vantage point than Earth-based telescopes, provided an unexpected service during the crisis. Because of the geometry of its orbit and its position relative to the Earth-Sun line, Stereo was able to observe Betelgeuse during a period when the star was too close to the Sun in the sky for ground-based telescopes to watch it without being blinded by solar glare. That continuous observational coverage, stitching together the ground-based data with Stereo data and the Hubble ultraviolet measurements, gave scientists something they had never had before for a dramatic stellar event: a genuinely complete, continuous observational record spanning the event from its earliest detectable precursors through its peak and into its aftermath. The serendipity of having those different instruments pointed at the right star at the right time is one of those moments where scientific infrastructure, accumulated over decades for entirely different reasons, pays dividends that nobody fully anticipated. The immediate speculation the media ran with that Betelgeuse was about to go supernova turned out to be incorrect, at least in any near-term sense. By March and April of 2020, the star began recovering. Its brightness climbed back toward normal levels. The crisis, such as it was, appeared to be passing, and the wave of popular interest that had briefly made Betelgeuse the most discussed astronomical object on the internet began to ebb. But the scientific community's work was just beginning, because the question of what had actually happened remained wide open, and the answer, when it arrived, turned out to be both more surprising and more scientifically significant than even a near-term supernova announcement would have been. Two competing hypotheses dominated the initial months of analysis, and the debate between them was not trivial. It had real implications for how scientists understood red supergiant behavior in general, not just Betelgeuse in particular. The first hypothesis centered on what's called a surface cool spot, or, more precisely, a region of the star's photosphere that had cooled significantly relative to its surroundings. Not cold by any human standard. We're still talking about gas at thousands of degrees. But cool enough relative to the rest of Betelgeuse's already relatively cool surface to noticeably reduce the brightness of that region. These cool patches are driven by the same convection process that makes the star pulsate. Giant cells of hot gas rise from deep within the star, cool as they approach the surface and radiate their energy away, then sink back down. In a star as enormous as Betelgeuse, individual convective cells can be larger than the entire sundae. A particularly large, particularly vigorous convective upwelling could bring a bubble of gas to the surface that's dramatically cooler than its surroundings, creating a dark patch, a stellar analog to a sunspot, but on a scale that makes actual sunspots look microscopic. The mathematics of this hypothesis worked reasonably well. A sufficiently large, sufficiently cool surface region in Betelgeuse's southern hemisphere could, in principle, account for the observed degree of dimming, and would also explain why the southern hemisphere appeared darker in the ESO surface images. Convective cells of the required scale are not implausible for a star of Betelgeuse's size. The star's interior is expected to have convective cells far larger than anything our Sun produces. This hypothesis was tidy, physically motivated, and didn't require invoking any processes beyond what was already understood about how red supergiants work. The second hypothesis involved dust specifically, dust formed from material ejected by the star that then condensed and blocked the starlight reaching Earth. Betelgeuse continuously sheds mass outward through its stellar wind, a stream of gas and particles flowing away from the star's surface at velocities that, while slower than the explosive ejection Hubble had detected, still amount to a substantial ongoing mass loss. Astronomers knew that Betelgeuse was surrounded by a complex circumstellar environment of gas and dust. Previous infrared observations had mapped this dusty cocoon in considerable detail. If an unusually large clump of gas were ejected from the star's surface and then, as it traveled outward and cooled, condensed into fine solid particles, that dust cloud could position itself between Betelgeuse and Earth along our line of sight. From our perspective, a significant fraction of the star's light would be absorbed or scattered by the dust before it reached us, dimming what we observe without the star itself necessarily changing its energy output. This hypothesis had its own strengths. The asymmetry of the dimming, the fact that it was concentrated in the southern hemisphere as seen in the ESO images, could be explained if the dust cloud happened to form preferentially on the side of Betelgeuse facing toward us from the south. And astronomers studying variable red supergiants in other contexts had invoked dust formation as a dimming mechanism before, so the concept wasn't novel. For much of 2020 and into 2021, these two explanations competed for primacy. Research groups published analyses supporting one interpretation over the other, or arguing for various combinations of the two. The scientific literature on Betelgeuse during this period reflects a community genuinely wrestling with what the data meant, with different teams drawing different conclusions from overlapping observational datasets. This is science working the way science is supposed to work, not a monolithic consensus handed down from authority, but a distributed, argumentative, evidence-driven process of trying to get closer to the truth. The resolution came in 2022 with a comprehensive study led by Andrea Dupree at the Harvard-Smithsonian Center for Astrophysics, published in the Astrophysical journal Letters. Dupree and her team assembled the most complete picture of what had happened by integrating data from Hubble's ultraviolet observations, ground-based visible light photometry, the ESO surface images, infrared measurements of the circumstellar dust, and the stereo data, the full multispectral, multi-instrument record that the fortuitous availability of all those different observing platforms had made possible. And what the integrated picture showed was something that neither the cool spot-only hypothesis nor the dust-only hypothesis could fully explain on its own. The great dimming, Dupree and her team concluded, was caused primarily by a surface mass ejection, the ejection of a massive chunk of the star's photosphere into space, in an event with no precedent in the observational record of any star. Here is what the evidence pointed to, in the sequence the observations implied. Somewhere beneath Betelgeuse's photosphere, the layer of the star that we see as its visible surface, a massive convective bubble of hot gas had been rising. Not merely a large convective cell of the kind that produces the star's normal pulsations, but something significantly more energetic. In the months before the visible dimming began, while Hubble was detecting that fast-moving hot gas streaming outward at 200,000 miles per hour, this bubble was approaching the surface with enough force to do something extraordinary. It broke through, not gently, not as a gradual upwelling. The bubble erupted through the photosphere with sufficient energy to physically launch a portion of the star's visible surface into space. The mass ejected in this event was estimated at roughly 2 to 4 times the mass of Earth's moon. Let that number sit for a moment. The moon, the natural satellite of Earth, the object that raises our tides, the body that Apollo astronauts walked on, has a mass of approximately 7.3 times 10 to the 22nd power kilograms. Between 2 and 4 times that amount of stellar material was torn away from Betelgeuse's surface and thrown outward into space in a single explosive event. This was not the ordinary stellar wind mass loss that Betelgeuse experiences continuously. This was a catastrophic, discrete expulsion comparable, in some ways, to having a small asteroid's worth of stellar material blasted off the star's surface in one violent, convulsive event. The comparison with our Sun's behavior is instructive and, frankly, humbling. Our Sun regularly produces what are called coronal mass ejections, violent expulsions of plasma from its upper atmosphere, often triggered by magnetic reconnection events in active regions near sunspots. These solar CMEs are taken very seriously by space weather researchers because a large CME directed toward Earth can disrupt satellite operations, GPS navigation systems, power grids, and radio communications. The Carrington event of 1859, the largest solar CME in recorded history, caused telegraph systems across North America and Europe to fail, with some telegraph operators reportedly receiving electrical shocks from their equipment. The storm induced currents in the telegraph wires strong enough to operate the machines without their batteries. Had the Carrington event occurred today, the economic damage from disrupted power and communications infrastructure could run to hundreds of billions of dollars. And yet, the Carrington event, the most powerful solar CME in the modern observational record, was dwarfed by the Betelgeuse surface mass ejection, not by a factor of 2 or 5, by hundreds of times. The mass Betelgeuse, ejected in the Great Dimming event, was several hundred times greater than the mass released in any recorded solar CME. What the Sun does periodically and dramatically, Betelgeuse did in a manner so extreme that it tore a chunk of its own visible surface away and sent it sailing into the surrounding space. The terms are the same: mass ejection, surface event, eruption, but the scales are so different that the comparison almost feels unfair, like describing both a campfire and a forest fire as burning. What happened next followed from the physics with a kind of straightforward, implacable logic. That ejected chunk of stellar material, once it separated from the star and began traveling outward through the space surrounding Betelgeuse, started cooling. The gas that had been at thousands of degrees on the star's surface began losing heat as it expanded and moved away from the source of warmth. As it cooled, the atoms and molecules within it condensed first into gas phase compounds. Then, as the temperature dropped further, into tiny, solid particles, silicates, carbon compounds, the kind of fine refractory materials that form in the cold outer regions of stellar atmospheres and in the circumstellar envelopes of evolved stars. Dust, in the astronomical sense, not the dust of ordinary human experience, but microscopic solid particles that collectively can block and scatter light very effectively when present in sufficient quantity. This dust cloud formed in the space around Betelgeuse, positioned between the star and Earth along our line of sight. From our perspective, a significant fraction of the star's light was being absorbed by this freshly formed, star-born cloud. At the same time, the region of the star's surface from which that mass had been violently torn was left in a disturbed state cooler than the surrounding photosphere because the violent upwelling had disrupted the normal convective circulation of hot material from below, leaving behind a region where the replenishment of heat from the interior was temporarily reduced. This cool patch reduced the light output from the southern hemisphere of the star, consistent with what the ESO images showed. The two effects compounded each other in a way that maximized the apparent dimming from Earth's vantage point. A dust cloud blocking light on the far side, combined with a cool surface region reducing emission from within, both working together to produce the deepest, most dramatic dimming of Betelgeuse in the historical record. The Great Dimming wasn't one thing. It was the observable signature of a stellar catastrophe that produced two simultaneous, reinforcing effects, and the coincidence, if coincidence is the right word, for something driven by physical necessity of both effects occurring together, and both reducing brightness from Earth's perspective, is what made the event so dramatically visible. The discovery of the surface mass ejection mechanism was not merely an explanation for a specific event. It was, in a deeper sense, the discovery of a type of stellar behavior that had never before been definitively documented. Solar coronal mass ejections were well understood. Stellar winds were well understood. The mass loss of red supergiants through their circumstellar envelopes was well studied. But a discrete, catastrophic surface mass ejection of this scale, a chunk of photosphere literally torn away and launched into space, had no confirmed prior example anywhere in the observational record. Betelgeuse had done something that, as far as we knew, no star had ever been caught doing before. And the implications for stellar physics extended far beyond understanding one unusual dimming event. To understand why the Great Dimming and its aftermath have generated the intensity of scientific attention they have, and why scientists are quietly panicking, is not entirely the exaggeration it might seem. You have to understand what Betelgeuse is actually approaching, not just in the abstract sense of a massive star approaching the end of its life, but in the specific, well-defined, physically predictable sense of a star moving through identifiable nuclear burning stages toward an inevitable and spectacular conclusion. Stars generate energy through nuclear fusion, the process of combining lighter atomic nuclei into heavier ones, releasing energy in the process. For most of a star's life, the fuel being fused in the core is hydrogen. Our Sun has been doing this for about 4.6 billion years and has roughly another 5 billion years of hydrogen fuel remaining. The process is astonishingly efficient in energy terms every second. The Sun converts approximately 600 million metric tons of hydrogen into helium through fusion, releasing the energy as light and heat, and even so, there's enough hydrogen fuel for a total lifetime of about 10 billion years. For a star like our Sun, hydrogen burning is a long, stable, gradually evolving process. For Betelgeuse, with its 10 to 20 times greater mass, the story is entirely different. Greater mass means greater gravitational compression of the core, which means higher core temperatures and pressures, which means faster fusion rates, which means the hydrogen fuel is consumed at a far faster rate. A star 10 times more massive than the Sun doesn't live 10 times longer, it lives far shorter, because it's burning its fuel far faster than the linear mass relationship would suggest. Betelgeuse blazed through its hydrogen-burning phase in a small fraction of the time our Sun has spent doing the same thing, and it has already moved on. When hydrogen runs out in the core of a massive star, gravity compresses the core until temperatures rise enough to ignite helium fusion, the process of fusing helium nuclei into carbon and oxygen. Helium burning produces energy, but less efficiently per unit mass than hydrogen burning, so the star has to work harder to maintain the outward pressure against gravity. It does so by running the fusion faster, which consumes the helium more rapidly than it consumed the hydrogen. When helium runs out in the core, in a star massive enough, carbon fusion begins, then neon, then oxygen, then silicon. Each successive stage burns faster and faster, because each fuel produces less energy per unit mass than the one before, and the star is compressing more intensely to maintain the fusion rate, which burns the fuel more rapidly. This acceleration of stellar burning in the late stages of a massive star's life is one of the most dramatic features of high-mass stellar evolution. The total hydrogen burning phase for a star like Betelgeuse might last millions of years. The helium burning phase, shorter. Carbon burning, shorter, still potentially lasting hundreds of years. Neon burning, perhaps a year. Oxygen burning, months. Silicon burning, days. The star burns through each successive fuel at an accelerating pace as it descends through the periodic table of elements toward iron, the end point of exothermic nuclear fusion, the element whose nucleus is so tightly bound that fusing it together doesn't release energy. It requires energy. When a massive star's core fills up with iron, the support against gravitational collapse simply stops. There is no next fuel to ignite. Gravity wins absolutely, in fractions of a second. Betelgeuse, at 8 to 8.5 million years old, and with a mass 10 to 20 times that of the Sun, has already burned through its hydrogen and is well into its later stage fuel cycles. The exact stage it's in, how many of those successive burning phases it has passed through, is difficult to determine from surface observations alone, because the information about what's happening in the core doesn't travel to the surface in a way astronomers can easily read. The outer layers of a red supergiant are enormous, turbulent, and optically opaque, making the core conditions essentially invisible to our instruments in most wavelengths. The star's outer appearance tells you about the outer layers, the photosphere, the chromosphere, the circumstellar envelope, but provides only indirect and uncertain clues about what's happening many stellar radii deep inside. This opacity cuts both ways. It means scientists cannot directly observe what fuel is currently burning in Betelgeuse's core, cannot verify whether the star is in the helium burning phase, the carbon burning phase, or some more advanced stage. But it also means that the star's eventual supernova will be preceded by essentially no visible warning at the surface. The core could be collapsing right now, at this very second, and the shock wave from that collapse wouldn't reach the visible surface of Betelgeuse for hours or days. The light from the explosion wouldn't leave the star until the shock wave broke through the photosphere. So even if the most dramatic stellar event possible is currently in progress inside Betelgeuse, we would not see it yet. We would not know until the light and the neutrinos arrived. Those neutrinos are, arguably, the most scientifically important aspect of any future Betelgeuse supernova, and understanding why requires a brief digression into one of the stranger particles in physics. Neutrinos are produced in enormous quantities by the nuclear reactions inside stars, including in the core collapse process that drives a supernova. They are electrically neutral, have almost no mass, though not precisely zero, and interact with matter through only the weak nuclear force and gravity, two interactions so feeble that a neutrino can, on average, pass through a light year of solid lead without hitting anything. They stream through ordinary matter as if it barely exists. They are passing through your body right now in vast numbers, billions per square centimeter per second, flowing from the sun without any of them interacting with a single atom in your body. You are transparent to neutrinos. So is the Earth. So is everything. This makes them both valuable and frustrating. Valuable because, unlike light, neutrinos don't get absorbed or scattered on their way out of a star's core. When a star's core collapses and produces a burst of neutrinos, those neutrinos leave the collapsing core immediately, passing straight through the star's outer layers, which light cannot do, taking thousands of years to diffuse from the core to the surface and arriving at detectors on Earth hours before the light from the explosion reaches us. Neutrinos are, in a very real sense, the first signal of a supernova. Frustrating, because detecting something that doesn't interact with matter requires building enormous quantities of matter and waiting for the rare, occasional interaction that does occur. Neutrino detectors are typically large tanks of water or ice, buried deep underground to shield them from cosmic rays that would otherwise overwhelm the faint neutrino signal. Instrumented with sensitive light detectors that can register the faint flash of light produced when a neutrino does, on rare occasion, smash into an atomic nucleus and produce a secondary particle that travels briefly faster than light, travels through the medium of water, a phenomenon called Cherenkov radiation, producing a blue glow analogous to the sonic boom of a supersonic aircraft, but in light rather than sound. The proof that this approach works came in 1987, with the observation of supernova 1987A in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, approximately 168,000 light-years away. When the massive star Sanduleak -69202 collapsed, the resulting neutrino burst was detected by 3 separate neutrino observatories around the world: Kamiokande 2 in Japan, the Irvine, Michigan Brookhaven detector in the United States, and the Baksan Neutrino Observatory in the Soviet Union. The total combined detection was approximately 24 neutrinos, arriving in a burst lasting about 12 seconds, several hours before the optical brightening of the supernova was visible. Those 24 particles, out of an estimated 10 to the 58th power neutrinos produced by the event, were the most direct confirmation ever obtained that a star had undergone core collapse, and they matched the theoretical predictions for the neutrino emission from a collapsing stellar core with remarkable accuracy. 24 neutrinos from a star 168,000 light-years away. Now consider what would happen if Betelgeuse at approximately 700 light-years, roughly 240 times closer than 1987A, were to go supernova. The neutrino flux at Earth would scale as the square of the inverse distance ratio, 240 squared, is roughly 57,600. Multiply that by the 24 neutrinos detected from 1987A, and you get an expected yield, in a detector the size of Kamiokande 2, of well over 1 million neutrinos from a Betelgeuse supernova. Modern detectors are larger and more sensitive than those available in 1987. The Super Kamiokande detector in Japan, which replaced the smaller Kamiokande 2, is expected to register hundreds of thousands of neutrino interactions from a Betelgeuse core collapse. Proposed next-generation detectors like Hyper Kamiokande would register even more. The data from those few seconds of neutrino detection would be the richest dataset in the history of stellar physics. More information about the internal dynamics of a collapsing stellar core than all previous observations combined. This is why multiple neutrino observatories around the world are currently connected to an alert system specifically designed to trigger notifications if they simultaneously detect an unusual spike in neutrino counts consistent with a nearby stellar core collapse. The network is called SNEWS, the Supernova Early Warning System. It links detectors on multiple continents, and its purpose is exactly what the name says: to provide as much advance warning as possible that a supernova has begun, so that the world's telescopes can be aimed at the relevant part of the sky within hours of the core collapse, maximizing the observational coverage of the earliest and most scientifically valuable phase of the explosion. SNEWS exists specifically because of the lessons learned from 1987A, the neutrino detectors. There happened to be running and happened to be looking at the data in time, but it was largely fortuitous. With SNEWS in place, if Betelgeuse's core collapses tonight, the astronomical community will know about it within minutes, and the world's telescopes will be pointing at Orion before the light from the explosion reaches Earth's surface. Now, we need to return to the direct aftermath of the Great Dimming, because what happened in the years following the 2019 to 2020 event continued to be scientifically extraordinary, and in 2023, it produced a development that, depending on how you interpret it, is either the most reassuring thing that could have happened or the most puzzling. After the Great Dimming, Betelgeuse's brightness recovered and returned approximately to its pre-dimming average by the middle of 2020. The star had lost, and then regained, its normal apparent brightness. The crisis, in the popular sense, was over, but astronomers tracking the star's pulsation cycles noticed something that lingered as a consequence of the event. Those well-established rhythms, the 400-day cycle and the 5-9-year cycle, that had been Betelgeuse's reliable signature variability for the entire observational record, were disrupted. The violence of the surface mass ejection had shaken the star's interior in a way that scrambled the timing of these oscillations. Think of the pulsation cycles as a pair of tuning forks vibrating at different frequencies, their combined sound creating a complex but recognizable pattern. The surface mass ejection was like striking both tuning forks hard with a hammer. The vibrations continued, but now out of phase, the pattern scrambled, the predictable combined sound replaced by a more complex, harder-to-read interference pattern. Astronomers trying to predict when Betelgeuse's next minimum brightness would occur, or its next maximum, could no longer rely on the templates that had worked for decades. The star was behaving according to the same basic physics, but its specific expression of that physics had been reset by the trauma of the Great Dimming event. Then came 2023, and the reversal nobody was expecting. Betelgeuse got bright. Not just returning to normal levels of brightness brighter than normal, reaching brightness levels that some observational accounts described as among the highest recorded in decades. The star that had dimmed dramatically in 2019 to 2020 was now, several years later, doing the opposite, reaching the other extreme of variability in a direction that had received far less public attention than the dimming, but was, from a scientific perspective, equally puzzling and equally informative. The explanation that most researchers found most plausible was mathematical. Betelgeuse's two disrupted pulsation cycles, the shorter to 400, day 1, and the longer, 5-9. Year 1 had both been thrown out of their usual phase relationship by the Great Dimming event. In 2023, those two cycles happened to align such that both were simultaneously producing a brightening contribution, their combined effect adding constructively in the same direction at the same time. The result was a brightness spike beyond the normal range of either cycle individually, an additive effect of two separate rhythms temporarily resonating in phase with each other. Under this interpretation, the 2023 brightness surge was a consequence of disrupted cycles, finding a momentary constructive alignment, not a sign of any new process within the star, just the mathematical consequence of scrambled rhythms temporarily pointing the same direction. This explanation is widely accepted, but it leaves an important question unresolved. If the pulsation cycles were disrupted by the Great Dimming, and then they produced an unusual bright period in 2023 as they reasserted themselves in new configurations, what does Betelgeuse's future variability look like going forward? Will the 400-day cycle return fully to its pre-2020 period and amplitude? Will the star settle into a new stable pattern of variability? Or has the surface mass ejection permanently altered the star's internal dynamics in ways that will produce unpredictable variability for years or decades to come? The honest answer is that nobody knows, and that uncertainty is not a failure of expertise, it's a reflection of how genuinely, without precedent, the whole sequence of events has been. There is also a subtler, more speculative reading of the 2023 brightening that some researchers have entertained, not as a consensus view but as a possibility that the data doesn't allow them to rule out entirely. In the very late stages of a massive star's life, The accelerating pace of nuclear burning in the core can produce changes in the star's overall luminosity and surface behavior on timescales of years to decades. The star's outer layers, responding to changes in the energy output from a more energetically burning core, can fluctuate in ways that don't fit the patterns established during the earlier, slower burning phases. If Betelgeuse is genuinely in a more advanced stage of its nuclear burning sequence than standard models predict, if it's already past the helium burning phase and into the faster burning stages, then the unusual variability of the last several years, including both the great dimming and the subsequent brightening, might be reflecting that advanced evolutionary state rather than being purely random fluctuations around a normal baseline. This interpretation remains speculative and contested. Many researchers caution strongly against reading too much evolutionary significance into short-term variability in a star as complex and turbulent as Betelgeuse. But the possibility cannot be dismissed entirely, and it's one of the reasons the monitoring programs have intensified rather than relaxed since the resolution of the Great Dimming's immediate drama. What a Betelgeuse supernova would actually look like, the experience of it from Earth, the physics of the event itself is worth dwelling on in considerable detail, because the reality is both more spectacular and, in most important respects, less threatening than popular imagination tends to render it. When the core of Betelgeuse finally collapses, and the word "when" is doing a great deal of work in that sentence, given that "when" could mean anywhere from a few thousand to 100,000 or more years from now, the sequence of events in the star will unfold with extraordinary rapidity by stellar standards. The iron core, which has been supported against gravitational collapse by the pressure from the silicon burning that produced it, will find itself unable to sustain further fusion reactions. Iron sits at the bottom of the nuclear binding energy curve. It takes energy to build anything heavier than iron by fusion rather than releasing energy. So when the core fills with iron, the outward pressure from energy-generating fusion simply stops. Gravity responds instantly. In less than a second, fractions of a second, the core, that had been supported by fusion pressure, collapses inward at speeds approaching a quarter of the speed of light, compressing from a ball of iron roughly the size of Earth to a sphere roughly the size of a city, perhaps 10 to 20 kilometers across. At those densities, the material can compress no further. The pressure from quantum mechanical effects, specifically from protons and electrons being squeezed together to form neutrons, creates a hard boundary that the collapsing core smashes into. The rebound of that collision sends a shock wave outward through the star's interior. The energy released in this process, the gravitational potential energy converted as the core compresses, is staggering, roughly equivalent to what our Sun will emit over its entire 10 billion-year lifetime, all concentrated into a few seconds. The outer layers of the star, not yet aware of what has just happened in the core because no signal can travel from the core to the surface faster than the physical propagation of the shock wave, are still doing what they were doing a fraction of a second ago, being a red supergiant. Then the shock wave arrives. It sweeps outward through the star's layers with enormous energy, compressing and heating the material it passes through, triggering new fusion reactions in some layers and simply blasting others away. The outer layers of the star are driven outward by this shock wave, initially at speeds of thousands of kilometers per second, and the star that had persisted for 8 million years is, in the span of hours, being torn apart from within. From Earth, the visible light from this event arrives hours after the neutrino burst, the delay being the time it takes the shock wave to travel from the core to the photosphere and break through. When it does break through, the optical brightening begins, and it does not proceed gently or slowly. Betelgeuse, currently one of the top 10 brightest stars in the night sky, would brighten by a factor of billions over the course of a few days, becoming something that has no analogue in modern human experience of the sky. Within days of the visible brightening beginning, Betelgeuse would reach a peak luminosity brighter than the full moon. Let that settle in for a moment. The full moon, on a clear night, is bright enough to cast visible shadows on the ground, bright enough to read large text by, bright enough to make the night sky appear a deep blue rather than black. Betelgeuse would surpass that. It would be the second brightest object in the sky after the Sunday. It would be visible in broad daylight, a brilliant blue-white point of light burning through the blue of the daytime sky in a way that no star has done in any human being's lifetime, or in any ancestor's lifetime for many thousands of years. At night, shadows cast by Betelgeuse would be sharper than those cast by the full moon. The Milky Way would be overwhelmed in the vicinity of Orion. The constellation itself would become unrecognizable, dominated by the blazing point in what used to be the right shoulder position. The last supernova that matched this kind of visibility was not in any living person's memory, or their grandparents' memory, or any ancestor's recorded experience. Kepler's supernova of 1604, the last supernova, confirmed to have occurred within our own Milky Way galaxy and been observed by human eyes, was visible during the day for a period of time after its peak. That event was far more distant than Betelgeuse's 700 light-years, yet it still briefly outshone every other star in the sky. A Betelgeuse supernova would be dramatically brighter than Kepler's supernova, visible in daylight for potentially weeks, dominant in the night sky for months. The brilliant naked-eye phase would eventually fade as the energy from the explosion dispersed and the expanding shell of gas and debris from the event spread outward. Over weeks, the brilliant point would soften. Over months, it would begin to acquire the slightly fuzzy, diffuse character of an extended object rather than a perfect point. Over years, the expanding nebula produced by the explosion would become large enough to resolve through telescopes, and astronomers would begin the detailed study of the supernova remnant, the cloud of ejected stellar material enriched with heavy elements created in the nuclear burning stages and in the explosion itself. This nebula would remain visible to telescopes for thousands of years, expanding and cooling and eventually merging with the surrounding interstellar medium, seeding it with the atoms that Betelgeuse spent 8 million years creating. As for the star's core, what gets left behind when the outer layers are blasted away depends on the star's mass. For a star in the lower part of the massive star range, the collapsed core settles into a neutron star, the densest ordinary matter object possible, roughly the mass of the Sun compressed into a sphere 10 to 20 kilometers across, so dense that a teaspoon of neutron star material would weigh billions of tons on Earth. Neutron stars often spin rapidly and emit beams of radio waves from their magnetic poles. These are the pulsars that radio astronomers detect as precisely timed pulses, stellar lighthouses rotating hundreds of times per second. For a star toward the higher end of the massive star mass range, the collapsed core may form a black hole directly, an object from which not even light can escape once it crosses the event horizon. Betelgeuse's mass range, 10 to 20 solar masses, with genuine uncertainty across that span, straddles the rough boundary between neutron star formation and black hole formation. Whether the Betelgeuse supernova leaves behind a pulsar we can study for millennia, enriching our understanding of dense matter physics, or collapses immediately into a black hole, leaving astronomers to study only the expanding nebula, is genuinely unknown. The answer depends on details of the star's internal structure that current observations cannot resolve. What it would not do is harm Earth. The dangerous zone for a supernova, the distance within which the radiation, the shock wave of high-energy particles, or a potential gamma-ray burst could damage Earth's biosphere, is roughly within 25 to 50 light-years. Betelgeuse sits at approximately 700 light-years. The margin of safety is not small, it is overwhelming. The radiation from the supernova will arrive at Earth as a slightly elevated level of X-rays and gamma rays, detectable by space-based observatories, interesting to scientists, and of no consequence whatsoever to biological life on the planet's surface. There will be no mass extinction, no damage to the ozone layer of any significance, no radiation health effects for any living thing, just the most spectacular light show in human history and the most scientifically rich astronomical event in the history of our species. The broader context of why Betelgeuse has attracted so much sustained scientific attention, why it has generated more papers, more monitoring resources, and more collective scientific focus than almost any other single star in the sky, extends beyond any specific dramatic event and into what the star represents for the whole enterprise of understanding how the universe works. For much of the history of stellar astrophysics, the theoretical models of how massive stars evolve and die were built on a foundation of indirect evidence. We could see stellar remnants, the nebulae and pulsars and black holes left after supernovae, and work backward from their properties to infer what the progenitor stars might have been like. We could observe massive stars in our galaxy and in nearby galaxies statistically, building population-level understanding of how such stars are distributed across evolutionary stages. We could run increasingly sophisticated computer simulations of stellar interiors, incorporating the nuclear physics, the fluid dynamics, the radiation transport, and the magnetic fields that all contribute to the behavior of these objects. But for most of the history of the field, the opportunity to observe a single nearby massive star in sufficient detail to test these models against reality in real time was extremely limited. Betelgeuse changes that. The closest red supergiant to Earth by a significant margin, close enough that its surface can be directly imaged, its pulsation cycles tracked over decades, its circumstellar environment mapped in detail across multiple wavelengths. Betelgeuse is the one gift the universe has given us of a supernova progenitor close enough to study with genuine resolution. What we learn from Betelgeuse propagates through all of stellar evolution science, because the physics operating in this star operates in every massive star, in every galaxy in the observable universe. The surface mass ejection discovery is the most direct example of this propagation. Before 2019, the mass loss of red supergiants was understood as a relatively continuous process, stellar winds carrying material away gradually, perhaps episodic enough to produce some variability in the rate, but not generating the kind of catastrophic, discrete, large mass ejections that the Betelgeuse event demonstrated. The SME finding forces a revision of mass loss models for red supergiants generally. If Betelgeuse can do this, and if Betelgeuse is not uniquely unusual among red supergiants, then the other red supergiants in our galaxy and beyond are presumably also capable of SME-type events. When they occur in those more distant stars, they might appear as unusual brightness variations, dimming events, asymmetric surface appearances that observers have been cataloguing without understanding their physical cause. The Betelgeuse case gives a physical model that can now be applied to those other observations. This also connects to a broader problem in stellar physics called the red supergiant problem. When astronomers look at the supernovae that occur in nearby galaxies close enough that the progenitor star, the star that exploded, can be identified in pre-explosion images taken years or decades earlier, they find a striking pattern. The most luminous red supergiants, the ones at the bright end of the red supergiant luminosity range, are conspicuously absent from the list of confirmed supernova progenitors. Supernovae are being produced by moderate luminosity red supergiants, but the most luminous ones seem to disappear from view without producing a detected supernova. One possible explanation is that these very luminous red supergiants collapse directly to black holes without producing the bright optical supernova event that would allow them to be detected. They go out not with a bang, but with a dimming, swallowing themselves rather than exploding outward. Betelgeuse, near the more luminous end of the red supergiant range, is therefore interesting not just as a future supernova candidate, but as a potential data point on whether the most luminous red supergiants behave differently from their less luminous cousins in their final stages. There is also the question of what the post-SME state of the circumstellar environment means for what observers will see when Betelgeuse eventually does explode. The material ejected in the 2019 surface mass ejection, plus all the material that has been shed through the star's stellar wind over its history, forms a complex, structured environment of gas and dust surrounding the star. When the supernova shockwave eventually expands outward from the explosion, it will plow into this circumstellar material. The interaction between the shockwave and the surrounding gas will produce additional emission, lighting up the pre-existing material as the shockwave heats it. The shape and structure of the circumstellar environment at the time of the explosion influences the appearance and evolution of the supernova remnant. Understanding the current structure of Betelgeuse's circumstellar environment, which the observational programs monitoring the star are actively mapping, is directly relevant to predicting what the supernova remnant will look like and how it will evolve. The observational infrastructure that has been built up around Betelgeuse reflects the scientific community's recognition of all of this. Monitoring programs now cover the star across a remarkable range of the electromagnetic spectrum, each wavelength range revealing a different aspect of the star's behavior and contributing a different layer to the complete picture. In visible light, professional astronomers and citizen scientists alike contribute to continuous photometric monitoring, measuring the star's brightness night after night, building the kind of dense, comprehensive data record that makes it possible to identify subtle changes before they become dramatic ones. The American Association of Variable Star Observers maintains a database of Betelgeuse brightness measurements going back many decades, and the contribution rate has increased significantly since the Great Dimming, as more observers around the world recognize the star's heightened scientific importance. An interesting feature of this data collection is the role played by amateur astronomers, people with backyard telescopes and a few $1,000s worth of equipment, contributing scientifically useful measurements that complement the data from million-dollar professional facilities. Stellar brightness monitoring is one of the few remaining areas in modern astronomy where amateur contributions remain genuinely valuable to professional research, and Betelgeuse is one of the prime examples. In infrared light, observatories measure the thermal emission from the dust surrounding Betelgeuse and from the star's own photosphere at longer wavelengths. The star's circumstellar envelope of dust and gas, built up over millions of years of mass loss through stellar winds and now augmented by the material from the Great Dimming's surface mass ejection, emits and absorbs light at infrared wavelengths in ways that reveal its temperature, composition, and spatial distribution. Changes in the infrared signature can indicate changes in the star's mass loss rate, which in turn may reflect changes in its internal state. The infrared data from before and after the Great Dimming showed a clear signature of new dust forming the ejected stellar material cooling and condensing consistent with the surface mass ejection model. In ultraviolet light, the Hubble Space Telescope and other UV-capable instruments monitor the star's upper atmosphere, the chromosphere, and the transition region between the chromosphere and the corona, where temperatures reach tens of thousands of degrees and where high-energy processes occur. UV observations are particularly valuable because the earliest phases of surface eruptions often appear first in the UV. The hot, fast-moving gas detected by Hubble in early 2019, months before the visible Great Dimming, is an example of a UV precursor that wouldn't have been detectable in ordinary visible light. Maintaining UV monitoring of Betelgeuse means that if another surface event begins, there's a chance of detecting its earliest precursors with enough lead time to alert other observatories and increase monitoring cadence before the event becomes visible to ground-based instruments. In radio waves, radio observatories probe the star's circumstellar environment in ways complementary to infrared studies. The distribution of gas and molecular material in the outer regions of the circumstellar envelope, far from the star's photosphere, can be mapped with radio interferometers, and the velocities of the outflowing material, measured through the Doppler shifts of molecular spectral lines, provide direct information about the mass loss rate and the dynamics of the circumstellar outflow. Changes in the radio flux indicate changes in the amount and distribution of ionized gas around the star. Through interferometric surface imaging with facilities like the Very Large Telescope, astronomers build up a record of how Betelgeuse's visible face changes over time, how convective cells come and go, how the brightness distribution across the disk evolves, and how the cool spot left by the Great Dimming event has developed in the years since. Each new interferometric observation adds to this visual record, which has no equivalent for any other red supergiant, and which is gradually building into a longitudinal dataset of how a massive star's surface behaves as it approaches the final stages of its life. Through spectroscopy, the analysis of the star's light spread out by wavelength into its constituent colors, astronomers measure the composition of the star's outer layers, the temperature structure of the photosphere and chromosphere, the velocity of gas at different depths, and the presence and abundance of specific molecules that can serve as thermometers and barometers for the stellar atmosphere. Spectroscopic monitoring is particularly sensitive to the velocity of material moving toward or away from Earth, since moving material Doppler shifts the wavelengths of its spectral features. When a convective upwelling pushes material toward Earth, the spectral lines shift slightly toward the blue. When material is moving away, they shift toward the red. Tracking these velocity signatures over time allows researchers to map the three-dimensional dynamics of the star's turbulent outer layers. All of this observational effort converges on a shared goal: understanding Betelgeuse well enough that when something starts to change, when the star enters a new phase, when another dramatic event occurs, when the approach of the final collapse begins to leave detectable signatures, the scientific community will be ready to observe it with every available instrument, to capture it in as much detail as the technology of the moment permits. The unknowns about Betelgeuse deserve their own detailed accounting because they are not minor gaps in an otherwise complete picture. They are fundamental uncertainties that affect everything downstream, and understanding what we don't know about this star is as important as understanding what we do. The star's exact mass remains genuinely uncertain, spanning a range from roughly 10 to 20 solar masses, depending on the measurement approach. This is not a small uncertainty, it's a factor of 2, and it matters enormously for predicting the star's future. A star at the lower end of this mass range will evolve more slowly than one at the higher end, will produce a supernova with somewhat different characteristics, and is more likely to leave a neutron star rather than a black hole as its remnant. A star at the upper end will evolve faster, produce a more energetic explosion, and may be more likely to collapse directly to a black hole. The mass uncertainty also affects estimates of where the star currently is in its evolutionary sequence. A more massive star burns through successive fuel stages faster, so a 2-0 solar mass Betelgeuse would be further along in its evolution than a 1-0 solar mass Betelgeuse of the same age. The distance uncertainty already discussed compounds this problem, with distances ranging from 430 to 700 plus light-years depending on the measurement method, and with different measurement methods giving inconsistent results that cannot currently be reconciled. Every physical quantity derived from the distance, true luminosity, true radius, true mass loss rate, carries corresponding uncertainty. This makes Betelgeuse simultaneously the closest and most observable red supergiant, and an object whose fundamental properties remain frustratingly imprecise. The inconsistency between different distance measurement methods is itself an active research problem, because resolving it requires either better instruments, more sophisticated modeling of the star's complex atmosphere, or some combination of both. The star's current nuclear burning stage, the single most important quantity for predicting how far from death it actually is, cannot be directly determined from any current observational approach. The opacity of the outer layers prevents direct observation of the core. The neutrino emission from the core, which in principle carries information about the nuclear reactions producing it, is so faint at Earth's distance, even for the copious neutrino production of Betelgeuse's interior, that current detectors cannot plausibly detect the steady-state neutrino output from the star. Only the brief, enormously intense neutrino burst of a core collapse would be detectable. So the question of what fuel is currently burning in the core of Betelgeuse, the most fundamental question for understanding the star's evolutionary stage, simply cannot be answered with current technology. Astronomers can constrain it based on stellar evolution models and on the star's surface properties, but the actual core cannot be observed. The mechanism that drove the 2019 surface mass ejection remains only partially understood. The broad outlines, a large convective bubble breaking through the photosphere and expelling material, are supported by the observational evidence, but the fine details remain unclear. What specific internal conditions produced a bubble large enough and energetic enough to cause a surface mass ejection of this magnitude? Was this a random fluctuation in the ongoing convective churning of the star's interior, or does it reflect some systematically different internal state compared to earlier decades when the star was observed without producing such an event? If it was random, could a similar or larger SME occur at any time? If it reflects a changed internal state, does that change point to an advanced evolutionary stage? These questions don't have confident answers yet. The future evolution of Betelgeuse's pulsation cycles, which were clearly disrupted by the Great Dimming, is uncertain. Theoretical models of how convective oscillations recover from major perturbations in red supergiants are not well enough constrained by observations of other stars to make confident predictions for Betelgeuse. Whether the star will return to something approximating its pre-2020 variability pattern, or will persist in a qualitatively different variability regime for years or decades, is unknown. This uncertainty makes it harder to interpret any unusual brightness behavior the star displays in coming years, because without a reliable baseline expectation to compare against, it's harder to determine whether an anomaly represents something scientifically significant or just the star's disrupted rhythms playing out. The history of supernova observations in human culture stretches back more than 1,000 years, and understanding that history helps illuminate how extraordinary a Betelgeuse supernova would be by comparison with every previous event of its kind that our species has witnessed. In 1054 CE, Chinese astronomers recorded the appearance of a guest star in the constellation we now call Taurus, an object that appeared where no star had been visible before, blazing brightly enough to be visible in daylight for weeks and to shine in the night sky for nearly 2 years before fading. Native American astronomical traditions also appear to have recorded this event in rock art. The guest star of 1054 was a supernova, and its remnant, the expanding shell of gas still visible today as the Crab Nebula, roughly 60 light-years across, and still expanding at more than 1,000 kilometers per second, nearly 1,000 years later, has become one of the most studied objects in modern astronomy. The Crab Nebula sits at a distance of roughly 6,500 light-years from Earth. Even at that distance, the supernova that created it was visible in daylight. Betelgeuse, a fraction of that distance away, would produce a display many orders of magnitude more dramatic. In November of 1572, the Danish astronomer Tycho Brahe was walking home from his laboratory when he noticed a star in Cassiopeia that he had never seen before. It was so bright that he initially disbelieved his own eyes, asking other people walking with him whether they could see it too. The star, now known as Tycho's supernova, or SN 1572, eventually became bright enough to be visible in daylight. Brahe made careful measurements of its position night after night, demonstrating that it showed no parallax relative to background stars as Earth moved, meaning it was far beyond the Moon, far beyond the planets, in the realm of the fixed stars. At the time, the prevailing Aristotelian view held that the celestial realm of the stars was perfect and immutable, incapable of change. Tycho's observations demolished this view. The heavens changed. Stars appeared where none had been. The cosmos was not perfect and eternal, and the observational evidence was written in the sky in letters bright enough to read in daylight. In 1604, just 32 years after Tycho's supernova, another appeared in the constellation Ophiuchus. This one was observed by Johannes Kepler, the same Kepler who would go on to formulate the laws of planetary motion, and it briefly reached a peak brightness comparable to or slightly exceeding Jupiter, making it, at its peak, the brightest star in the sky. Kepler's supernova remains the last supernova confirmed to have occurred within the Milky Way and been observable to the naked eye. That was 421 years ago. No human being alive today, and no human being in many generations before us, has ever seen a naked-eye supernova in our own galaxy. The last one happened before the Pilgrims reached America, before Galileo pointed his telescope at the sky, before Newton formulated the laws of mechanics and gravitation. A Betelgeuse supernova would end that 4-century drought in the most spectacular way possible. At 700 light-years, roughly a tenth of the distance of the typical supernova, it would produce a display that would make Kepler's supernova look modest by comparison. The magnitude difference between Kepler's supernova at its peak and a Betelgeuse supernova at its peak, given the distance difference, would be enormous. Every human being on Earth with functioning vision who was outside during the event would be aware of it. It would be the defining astronomical moment of recorded history. The scientists who study Betelgeuse are, as professionals, cautious people. They deal daily with the humbling scope of astronomical timescales, with the uncertainty inherent in studying objects billions of times more massive than anything humans can directly interact with, from distances that make the concept of close entirely relative. When asked whether Betelgeuse is about to explode, their careful, calibrated answer is, probably not in any human-relevant time frame. The estimates range widely, and the current data does not definitively constrain which end of the range is correct. And yet, the level of activity in the Betelgeuse research community since 2019 is not the activity of a community that has found a comfortable, steady state in its understanding of the object. It's the activity of a community that has been surprised, has updated its models in response to that surprise, and is now watching more carefully than before because they've learned that this star is capable of behavior they did not fully anticipate. The great dimming was not predicted. The surface mass ejection mechanism was not in the standard models. The subsequent brightness surge was not anticipated. Each of these developments has been explained in retrospect, fitted into a physical framework that makes sense of the observations. But explaining them in retrospect is different from having predicted them in advance, and the distinction matters. When a star that is supposed to be in the slow, steady decline toward its eventual death demonstrates repeatedly that it can produce dramatic, unexpected behavior at the surface level, the reasonable scientific response is to watch it more carefully and to approach the standard models with more humility. That is precisely what the community is doing. Research groups are revising stellar evolution codes to incorporate surface mass ejection processes that were previously absent or inadequately modeled. Theorists are developing better treatments of convection in red supergiant envelopes, convection being the physical process at the root of the pulsations, the surface mass ejections, and much of the unusual variability. Observational programs are being extended, intensified, and supplemented with new instruments. The quiet panic that some external observers have detected in the community's behavior is, from the inside, better described as heightened alertness grounded in genuine scientific uncertainty. These researchers know what this star is capable of. They know it did something in 2019 that their models didn't predict. They know its internal state, the most important factor for predicting its future behavior, is largely opaque to direct observation. They know that when this star does eventually undergo core collapse, the event will be so scientifically valuable that missing it, or being poorly positioned to observe it, would be a failure of scientific preparation with no remedy. And they know that their best current estimate of when the event will occur spans a range so wide that it cannot be used as a reliable guide to when to pay most attention. The rational response to all of these constraints is to pay maximum attention all the time. That is what the monitoring programs represent, not panic, but the kind of careful, sustained, resource-intensive attention that the scientific community can only justify when the potential payoff the data that would come from a well-observed Betelgeuse supernova is commensurate with the effort. The potential payoff here is, in the estimation of most researchers who work in high-mass stellar evolution, about as large as astronomical payoffs get. Consider what it would mean, scientifically, to observe the complete supernova of Betelgeuse with modern instrumentation. The neutrino burst would provide, for the first time with genuinely large number statistics, a direct observational test of core collapse models. With hundreds of thousands of neutrino events expected in Super-Kamiokande alone, compared to the 11 events that detector's predecessor recorded from SN 1987A, the neutrino data would constrain the downed temperature and density of the collapsing core with precision that no theoretical model has been tested against. The question of whether the collapse produces a neutron star or falls directly into a black hole would likely be answerable from the neutrino emission profile. A neutron star formation should produce a relatively long neutrino signal as the proto-neutron star cools over several seconds, while a direct black hole formation might produce a brief burst followed by an abrupt cutoff as the event horizon forms and swallows the neutrino-emitting surface. If gravitational wave detectors like LIGO and Virgo are operating at the time of the collapse, not a certainty, given that these facilities have maintenance periods and operational interruptions, the core collapse of a star at 700 light-years might produce a detectable gravitational wave signal. At 1987 A's distance, gravitational waves from the collapse would not have been detectable, even if LIGO had existed in 1987. At 700 light-years, the prospects are better, though not guaranteed. Depending on how asymmetric the collapse actually is, symmetric collapses produce less gravitational wave emission than asymmetric ones. A detected gravitational wave signal from Betelgeuse's collapse would be the first confirmed observation of gravitational waves from a stellar core collapse, providing information about the dynamics of the collapse itself that is completely inaccessible through electromagnetic observations. The optical evolution of the supernova would be followed from its very first moments, the shock breakout phase, when the blast wave first breaks through the star's photosphere, which for a red supergiant is predicted to produce a brief, intense, ultraviolet flash lasting minutes to hours. No supernova shock breakout has ever been observed from its very first second in a star as well characterized as Betelgeuse would be. The very first flash of light from the explosion, the signal that would trigger every telescope on Earth and in space to point at Orion, would itself be scientifically extraordinary. The subsequent optical evolution would be followed night by night, week by week, month by month, with spectroscopy revealing the composition and velocity of the expanding ejector, photometry tracking the decay of the light curve, infrared imaging mapping the dust that forms in the expanding remnant, and radio observations probing the interaction of the expanding shock wave with the circumstellar material that Betelgeuse has been shedding for the last 8 million years. The monitoring programs already in place for Betelgeuse, the networks of telescopes, the alert systems, the coordinated observation plans would be immediately activated and expanded. There would be no lag time, no scrambling to point instruments at a newly discovered supernova. The world's scientific community would be watching Betelgeuse before, during, and after the event, with a comprehensiveness of coverage that no previous supernova has ever received. It's worth stepping back from the science for a moment and considering what kind of thing Betelgeuse actually is in the full sense, not just as a scientific object, but as a part of the universe that our universe has been building for longer than human civilization has existed. Betelgeuse formed from a cloud of gas and dust in the Milky Way 8 to 8.5 million years ago. At that time, our hominin ancestors were upright walking primates in Africa, millions of years from becoming anything that would look up at the night sky and wonder what the lights meant. The star ignited, began fusing hydrogen in its core, and started its accelerated journey through stellar life. Long before the first human being constructed a tool, long before the first language was spoken, long before the first cave painting was made, Betelgeuse had already burned through its hydrogen-burning phase and settled into the enormous, turbulent, slowly cooling body of the red supergiant it remains today. Every photon of light streaming from Betelgeuse that reaches your eye tonight was generated in the thermal glow of the photosphere, that violent, churning surface layer where convective cells the size of the sun churn and roil, carrying energy upward from the nuclear fire in the core and releasing it as the light and heat that travels 700 light-years to reach you. The individual atoms in the gas that's glowing are themselves products of the star's nuclear-burning helium, carbon, oxygen, all the elements Betelgeuse has been forging in its core over 8 million years, mixed by convection into the outer layers where they become part of the visible, radiating surface of a living star. When Betelgeuse eventually explodes and scatters all of that material across dozens of light-years of space, the atoms it disperses will eventually become part of new star-forming clouds. Some of those atoms will find their way into new stars. Some will end up in rocky planets orbiting those new stars. And some of them, over billions of years of geological and chemical evolution on some of those planets, might end up in living things, might end up in cells, in proteins, in nucleic acids. The atoms in your body were made in stars, not in Betelgeuse, which hasn't exploded yet, but in stars that lived and died before the solar system formed. Stars that went through the same sequence Betelgeuse is currently in. When Betelgeuse finally goes supernova, it will complete the stellar cycle of creating heavy elements through nuclear burning and returning them to the universe to seed the next generation of stars and planets, and perhaps living things. That is not poetry, that is nucleosynthesis and stellar evolution, expressed in the most personal possible terms. The red star burning in Orion tonight is, in the most literal chemical sense, a factory, manufacturing the raw materials for future worlds. It has been doing this for 8 million years, and it will continue doing it until the moment its core collapses and it disperses itself across interstellar space in the most extravagant act of generosity the universe offers. In the years since the Great Dimming, the scientific literature on Betelgeuse has expanded enormously. Papers on the star appear regularly in the major astrophysical journals: Nature, the Astrophysical Journal, Astronomy, and Astrophysics, monthly notices of the Royal Astronomical Society. Each new paper adds another layer to the picture, constraining some uncertainty, opening new questions, proposing alternative interpretations of existing data, or reporting new observations that must be accommodated by existing models. The community of researchers actively working on Betelgeuse has grown substantially since 2019. Researchers who had focused on other areas of stellar astrophysics found themselves drawn to the star by the dramatic events of the Great Dimming. Instrumentalists proposed new observing programs. Theorists developed new models incorporating the surface mass ejection mechanism. Archival researchers went back through decades of historical observations to look for any earlier hints of unusual behavior that might have been overlooked when Betelgeuse was considered a relatively quiescent, if interesting, variable star. The Great Dimming functioned, in a sense, as an advertisement for Betelgeuse. It drew attention to the star from researchers who might otherwise have focused elsewhere, and many of them stayed. International collaboration has been central to this research effort. The data assembled around the Great Dimming came from instruments operated by NASA, ESA, ESO, national observatories in Japan, China, Russia, Australia, and many other countries. The SNEWS Neutrino Alert Network links detectors in Japan, the United States, Canada, Italy, and other countries. Variable star monitoring networks coordinate observers across every inhabited continent. Betelgeuse has become, in a small way, one of those scientific objects that functions as a point of common scientific purpose, a thing so interesting and so consequential that it transcends the normal institutional and national boundaries that usually compartmentalize scientific effort. This international character of Betelgeuse research reflects something true about modern astronomy more broadly, but it also reflects the particular urgency of the Betelgeuse situation. No single institution, no single country, no single telescope has the full set of capabilities needed to comprehensively monitor a star across all wavelengths and around the clock. The Southern Hemisphere observatories in Chile and Australia can observe Betelgeuse in ways that Northern Hemisphere facilities cannot during certain times of year. Space-based observatories provide access to wavelengths the atmosphere blocks. Radio observatories contribute complementary information to optical facilities. A truly comprehensive monitoring program for Betelgeuse requires all of these working together, sharing data, comparing results, and building the integrated picture that no single facility could produce alone. There is a quieter dimension to this story that doesn't appear in the scientific papers, but that anyone who has spent time talking to the researchers involved will recognize. The scientists studying Betelgeuse are, on some level, working toward witnessing something that they will almost certainly never see. The expected supernova is far enough in the future, almost certainly thousands to tens of thousands of years away at minimum, that no one alive today will be present when it occurs. The monitoring programs being built now, the alert systems being refined, the observational infrastructure being expanded and maintained, all of it is, in one sense, preparation for an event that the people doing the work know they will not be around to see. This is not unusual in science. Physicists build accelerators, knowing that the discoveries made will be made by the next generation of researchers. Biologists map genomes, knowing that the medical applications will be developed by people not yet born. But there's something particularly resonant about the astronomical version of this. The building of observational infrastructure for an event whose timing cannot be specified more precisely than somewhere in the next few 1,000 to 100,000 years, undertaken by people who will live perhaps 80 years. The timescale mismatch is so extreme that it forces a different kind of relationship between the scientist and their work. The goal is not personal discovery, it is institutional readiness. It is ensuring that when the moment comes, whenever the moment comes, the scientific community of that era will be the inheritors of a monitoring program with decades or centuries of accumulated data, an alert system that will respond within seconds of the first neutrinos arriving, and a community of researchers trained in the specifics of Betelgeuse science because previous generations maintained the attention and the knowledge. This is a form of scientific generosity operating on timescales that humans are not particularly well adapted to appreciate. Most human endeavors are calibrated to produce results within a human lifetime, or at most a few generations. The Betelgeuse monitoring enterprise is calibrated to produce its greatest results at an unknown future moment that might be 10 generations from now, or 50, or 500. The people building the foundation are doing it for people they will never meet, in a century they will never see, for a scientific return they will never personally collect. On any given clear winter night, anywhere in the northern hemisphere, you can walk outside after dark and see Betelgeuse. You don't need a telescope, you don't need any equipment at all. You just need to look for Orion, one of the most recognizable constellation patterns in the human sky. 3 bright stars in a row forming the belt, with brighter stars marking the shoulders and knees of the mythological hunter. The reddish-orange point at the upper left of the constellation, positioned at Orion's right shoulder as you face it from Earth, is Betelgeuse, one of the nearest true monsters of our stellar neighborhood, a dying giant burning its last fuels, shedding its outer layers into space, its face scarred by the explosive ejection of its own surface material, its rhythms disrupted and unsettled, watched by more eyes and instruments than at any previous moment in its 8 million-year existence. The light arriving at your eye right now left that star approximately 700 years ago. It has been traveling across the vacuum of interstellar space since roughly the time of the Black Death, or the reign of Edward III of England, or the compilation of the travels of Marco Polo. It traveled through the cold dark of space without interacting with anything, at 186,000 miles per second, for 700 years, and it arrived at the surface of Earth and entered your eye in the same instant that you happen to be standing outside, looking at the sky. The universe is full of these transactions, these improbable coincidences of photon and retina, but none of the others involves a photon from a star that is this actively in the process of doing something that scientists have never seen a star do before. There is something worth carrying with you from this story that goes beyond the specific science. The fact that Betelgeuse surprised the scientific community in 2019 that a star studied continuously for decades, with a well-documented history of variability, the subject of thousands of papers and decades of monitoring, still managed to do something genuinely unexpected, is itself important. It's a reminder that the universe is more varied, more surprising, and more full of physical processes we don't yet fully understand than any snapshot of current scientific knowledge can capture. The standard models are not wrong in any fundamental sense. The physics of stellar evolution is not in doubt. But the physics operates in systems of such complexity, with such extreme physical conditions, that even our best models are incomplete guides to what any particular star will do at any particular time. Betelgeuse will go supernova. The physics is certain, the timeline is not. And in the gap between those two certainties, the certainty that it will happen and the uncertainty of when, lies the whole enterprise of watching, waiting, measuring, and preparing that has made this single nearby red giant one of the most closely monitored, most actively researched, most scientifically consequential objects in the modern astronomical sky. Every winter, it rises above the horizon and crosses the night sky, burning its ancient fuel, shedding its mass, disturbing its own surface with convective upwellings of incomprehensible scale. Every winter, the monitoring programs take their measurements. The research groups analyze their data, and somewhere in a university office or a telescope control room, a scientist looks at the latest brightness measurement and compares it to what was expected, and notes whether anything unusual is happening. Most nights, the answer is nothing dramatic. The star is doing what the star does. The pulsations continue in their disrupted post. 2020 configuration. The stellar wind blows mass outward into the circumstellar envelope. The photosphere churns with convective cells that dwarf the Sun, and the 700-year-old light streams toward Earth at the speed of light, arriving at the rate of billions of photons per second for every square centimeter of telescope mirror aimed in its direction. And then, someday, some winter night, that no one alive today will be present to experience a neutrino detector somewhere in the world, will register an unusual spike. The snooze alert will go out. The telescopes will slew. And Orion's shoulder will catch fire in a way that nobody looking up at the sky will be able to ignore. A blue-white point blazing through the sky brighter than anything that has shone there in 1,000 years. And the most valuable few weeks of data in the history of stellar astronomy will begin to pour in from every instrument humanity has managed to point at the right place at the right time. That is Betelgeuse. That is why scientists are paying very close attention. And that reddish point of light you can see in Orion's shoulder on any clear winter night is one of the universe's most elaborate reminders of how strange, how large, how old, and how magnificently unfinished everything still is. Look up at it tonight if you get the chance. Know what you're actually seeing, not just a star, but a massive, ancient, dying, surprising, closely watched, scientifically irreplaceable object that has been building toward a conclusion for 8 million years. The light reaching your eyes right now set out from that star in the 14th century. It has earned the few seconds you can give it. Let's go deeper into the physics of what it actually means to be a red supergiant, because the category itself is one of the universe's more dramatic achievements, and most descriptions of it skim past details that fundamentally change how you understand what Betelgeuse is and what it's doing. Stars spend most of their lives in what astronomers call the main sequence, a stable, hydrogen-burning phase where the balance between gravitational compression and nuclear pressure holds steady for millions or billions of years. For our Sun, that equilibrium has lasted 4.6 billion years and will last another 5 billion or so. But the transition off the main sequence, when the core's hydrogen is exhausted, is one of the most dramatic changes a star can undergo. The core, no longer generating energy through hydrogen fusion, begins to contract under gravity. This contraction heats the core, eventually igniting helium fusion, but the heating also affects the star's outer layers in a counterintuitive way. Instead of contracting along with the core, the outer envelope expands enormously. The star grows. It cools at its surface, As the heat spreads over a vastly larger area, it reddens, and it becomes something recognizable, a giant. For Betelgeuse, this process happened millions of years ago, and the star didn't just become a giant, it became a supergiant, the most extreme end of the stellar evolutionary spectrum. The outer layers of the star expanded to hundreds of times the star's original main sequence radius. The surface temperature dropped from whatever it was during the hydrogen-burning phase, probably tens of thousands of Kelvin, for a star this massive to the current approximately 3,500 Kelvin, that gives Betelgeuse its distinctive reddish-orange color. At the same time, the core contracted and heated to temperatures where successively heavier elements could be fused, the star's nuclear burning program advancing stage by stage, while the visible outer envelope swelled to its current enormous size. The result is a structure that looks nothing like what most people picture when they imagine a star. The Sun, for all its immensity, compared to anything human scale, is relatively compact, a dense ball of plasma with relatively uniform density from core to photosphere, though the core is obviously much denser than the outer layers. Betelgeuse, by contrast, is more like a very tenuous cloud with a small, extremely dense, extremely hot core buried deep inside. The outer layers are so extended and so diffuse that they have a density well below what would be considered a good vacuum in a laboratory on Earth. The outer portions of Betelgeuse's atmosphere are genuinely less dense than the Earth's atmosphere at typical cruising altitude for a commercial aircraft. You could, in principle, fly a plane through the outer portions of Betelgeuse's atmosphere. You would be destroyed by the heat almost immediately, but the density wouldn't impede you. This counterintuitive looseness of the outer layers is part of why the surface mass ejection of 2019 was physically possible. In a compact, dense star, a convective bubble breaking through the photosphere might produce a modest eruption that quickly settles back. In Betelgeuse, where the outer layers are so weakly bound gravitationally, the gravitational pull at the photosphere of a star this extended is much weaker than the surface gravity of denser, more compact stars. A sufficiently energetic upwelling can genuinely launch material outward with enough velocity to escape the star's gravitational pull entirely. The star's own weakness, its looseness, its extended diffuseness, is precisely what makes these extreme surface events possible. Understanding this also helps explain why Betelgeuse loses mass so readily through its stellar wind. The stellar wind of a star is driven by radiation pressure, the pressure exerted by photons streaming outward from the hot stellar surface, pushing on the atoms in the outer atmosphere and accelerating them outward. In a compact, dense star with strong surface gravity, this radiation pressure has to work against strong gravity to drive material off the surface, and the resulting stellar wind is relatively modest. In a red supergiant like Betelgeuse, where the surface gravity is much lower, even moderate radiation pressure can drive substantial mass loss. Betelgeuse loses roughly 1 solar mass of material every 10,000 years through its stellar wind, which sounds modest until you realize that the Sun, with its weaker wind, loses that much mass every 100 billion years or so, roughly 10 times the age of the universe. Betelgeuse loses mass 10,000 times faster than the Sun does, and it has been doing so for millions of years, building up an enormous circumstellar envelope of gas and dust that extends far beyond the star's visible photosphere. This mass loss is not a minor detail. It is one of the ways the star interacts with the broader interstellar medium, seeding the space around it with material that will eventually become part of new clouds, new stars, new planetary systems. And it affects the star's own evolution as Betelgeuse sheds mass. Its total mass decreases, which affects the balance of forces in its interior, which influences the pace of nuclear burning and the timeline of its evolution towards supernova. Mass loss is a coupling between the star's interior and the interstellar environment, and it operates on a scale and at a rate that has no solar equivalent. The history of how astronomers came to understand the lives and deaths of massive stars is a story of accumulated evidence, theoretical breakthroughs, and occasional stunning observational windfalls. It's worth tracing briefly because it contextualizes both what we know about Betelgeuse and what we still don't. In the early 20th century, the basic understanding that stars generate energy through nuclear fusion was not yet established. The debate over what powered the Sun gravitational contraction, chemical combustion, some unknown source, was one of the outstanding problems of physics. The breakthrough came in 1938, when Hans Bethe worked out the carbon-nitrogen-oxygen cycle for hydrogen fusion in massive stars, and independently clarified the proton-proton chain for less massive stars like the Sunday. Bethe's work, which would earn him the Nobel Prize in Physics in 1967, established for the first time that nuclear fusion could sustain a star's energy output for the billions of years that geological and biological evidence implied the Sun had been shining. Once nuclear fusion was understood as the energy source, the question of stellar evolution, how stars change over time as they consume their fuel, became tractable. The theoretical framework for stellar evolution that emerged over the following decades was built on the coupled equations of nuclear physics, fluid dynamics, radiation transport, and gravity that describe the interior of a star in sufficiently simplified terms to be mathematically solvable. By the 1960s, the broad outlines of how stars of different masses evolved from birth to death were established. Low-mass stars would become white dwarfs after a red giant phase, while massive stars would undergo core collapse and explode as supernovae. The critical test of these theoretical models came in February 1987, when the blue supergiant Sanduleak 69, 202 inches, the Large Magellanic Cloud, exploded as supernova 1987A. This was the first supernova visible to the naked eye since Kepler's supernova of 1604, and it was the first one to occur when the modern observational infrastructure neutrino detectors, satellite observatories, radio telescopes, was in place to observe it. The results were largely consistent with theoretical predictions, but not perfectly so. The progenitor star turned out to be a blue supergiant rather than the red supergiant the models had predicted would be the immediate precursor of a core collapse supernova, suggesting that stellar evolution in the Large Magellanic Cloud's lower metallicity environment, the LMC, has a lower abundance of heavy elements than the Milky Way, which affects stellar evolution, could produce blue supergiant progenitors instead of red ones. The neutrino burst was detected as predicted, with timing and energy consistent with core collapse. The optical light curve behaved in ways mostly consistent with models, though with some deviations that required theoretical adjustment. SN 1987A remains the most studied object in the history of stellar astrophysics. Decades later, researchers continue to publish papers about it as the expanding remnant evolves and becomes accessible to observation at new spatial scales. The ring of material illuminated by the explosion's ultraviolet flash, pre-existing circumstellar material shed by the progenitor star in its earlier evolutionary stages, has been lit up and shaped by the expanding shock wave in ways that test models of supernova circumstellar interaction in real time. In a sense, SN 1987A has given the scientific community a 3-8-year and counting natural experiment in what happens after a massive star dies. Betelgeuse, when it eventually goes, will be the successor to 1987A, the next episode, in this natural experiment, conducted at a distance 240 times closer, with instrumentation 38+ years more advanced, monitoring programs already in place, and the advantage of knowing exactly what star was there before the explosion. The scientific returns will be proportionally larger. One of the more unsettling aspects of Betelgeuse's situation for people who find comfort in celestial predictability is the question of whether the star has already exploded and we simply don't know it yet. Given the approximately 700 light-year distance, the light and neutrinos from any event at Betelgeuse would take 700 years to reach Earth. So if Betelgeuse's core collapsed tonight, we wouldn't know for 700 years. Conversely, if Betelgeuse's core collapsed 700 years ago in the 1320s, approximately then the neutrinos and optical brightening from that event are currently racing toward Earth at the speed of light and will arrive at some point in our future, possibly centuries from now, possibly decades, possibly sooner. This is not a concern that astrophysicists lose sleep over, because the probability of the core collapse having happened within the last few hundred years is extremely low given the expected timescales involved. But it illustrates, in a rather visceral way, how different the experience of the universe becomes when you're dealing with astronomical distances. The star you can see in the sky is not the star as it currently is. It's a portrait of the star as it was in the past, a temporal as well as spatial displacement. When we talk about the current state of Betelgeuse, we're really talking about the state it was in when the most recent light we've received from it left the star. The actual current state, happening right now, in whatever stellar physics means by right now across interstellar distances, is inaccessible to us. This temporal displacement applies to everything we observe beyond Earth. The nearby star Alpha Centauri, the closest star system to our own at about 4.3 light-years, appears to us as it was 4.3 years ago. Sirius, the brightest star in the night sky, at 8.6 light-years, appears as it was 8.6 years ago. And Betelgeuse, at 700 light-years, appears as it was 700 years ago. When astronomers talk about understanding the current evolutionary stage of Betelgeuse, they're doing so with the caveat that the current they're assessing is 700 years in the past, and the star has continued evolving in the interim in ways they cannot directly observe. This caveat matters most in the context of rapidly changing late-stage stellar burning. If Betelgeuse is currently in the silicon burning phase, that phase lasts only days. If the core collapse followed the silicon burning, it would have followed within days of a stage that, from Earth, would appear as a 700-year-old state we cannot directly observe. The speed of the late-stage burning phases, days, months, years, compared to the 700-year light travel time, means that the star's internal state could, in principle, be at an entirely different stage of evolution from what the current observable surface state implies. The surface of a red supergiant doesn't immediately reflect changes in the core. The diffuse outer envelope is largely disconnected dynamically from the deeply buried core, so even the most carefully observed surface properties of Betelgeuse might not reveal that the interior had dramatically advanced in its evolutionary state. This is one of the reasons the neutrino detection network is so important. When the core collapses, the neutrinos will arrive at Earth with only a few hours delay relative to the optical brightening, not a 700-year delay. Because neutrinos are generated in the collapse itself and travel at nearly the speed of light from the moment of formation. They don't have to diffuse through the star's opaque outer layers the way photons generated in the core would. A neutrino burst arriving at Earth would be the first genuine real-time information about Betelgeuse's core information that corresponds to what the core is doing now, within the constraint of the speed of light and the 700-year baseline. Thinking about Betelgeuse in the context of the full galactic population of massive stars adds another layer of significance to what we can learn from it. The Milky Way galaxy contains hundreds of billions of stars. The fraction that are massive enough to eventually explode as core collapse supernovae is estimated at roughly 1 per every 1,000 stars, give or take. Depending on the initial mass function, the distribution of masses at which stars are born. That means the galaxy contains perhaps hundreds of millions of stars that will, at some point in their future, explode as supernovae. At the current rate of supernovae in galaxies like the Milky Way, roughly 1 to 3 per century, estimated from surveys of supernovae in other galaxies, the galaxy is producing supernovae regularly, but no galactic supernova has been observed since Kepler's in 1604. Why has there been no observed galactic supernova in over 400 years? Partly bad luck, the expected rate means a gap of 400 years is not statistically extraordinary, just somewhat unlucky. But also, importantly, obscuration. The Milky Way is a disk galaxy, and our solar system sits within that disk, surrounded by gas and dust that absorbs visible light very effectively. Supernovae, occurring on the far side of the galaxy, or behind dense molecular clouds, would be invisible in optical wavelengths, no matter how bright they were in absolute terms. In fact, supernovae are almost certainly occurring in the Milky Way right now, on the other side of our galaxy, completely invisible to optical telescopes from Earth, but potentially detectable by gamma-ray, X-ray, or radio observatories. The handful of supernova remnants detected in radio and X-ray surveys of the galactic plane include some that have no corresponding optical historical record, suggesting they occurred behind obscuring dust clouds. Betelgeuse, at 700 light-years in a relatively clear direction of the sky, is not obscured in this way. Its supernova would be visible in all its optical splendor. Other nearby massive stars within a few thousand light-years are also monitored and studied, though none with the intensity focused on Betelgeuse. The star Antares in the constellation Scorpius is another red supergiant of comparable size and evolutionary stage, somewhat more distant than Betelgeuse and therefore less accessible to surface imaging, but similarly studied as a supernova candidate. The star VY Canis Majoris is an example of an even more extreme red supergiant, one of the largest known stars, undergoing episodes of dramatic mass loss. The study of these and other red supergiants is informed by what researchers learn from Betelgeuse, and the findings from Betelgeuse, particularly the surface mass ejection mechanism, are reinterpreted in the light of observations of these other systems. In a broader statistical sense, every core collapse supernova observed in nearby galaxies was, at some point before its explosion, a star like Betelgeuse, a massive evolved star, sitting in the shoulder of some alien constellation, watched or unobserved, as the case may have been, burning its final fuels. In several dozen nearby galaxy supernova events, researchers have gone back through archival Hubble Space Telescope images and identified the progenitor star, the star that was there before the explosion. Almost all of the identified progenitors are red supergiants, though as noted earlier, the most luminous red supergiants are underrepresented among identified progenitors, giving rise to the red supergiant problem. Betelgeuse sits in or near the luminosity range where this underrepresentation begins, making its eventual fate: will it explode as a normal bright supernova, or will it collapse differently, particularly relevant to resolving that mystery. The question of what happens to matter after Betelgeuse's supernova deserves its own extended treatment, because the aftermath of a stellar explosion is as rich and as scientifically consequential as the explosion itself. In the immediate aftermath of the core collapse, the outer layers of the star, billions of kilometers of stellar material that had constituted the red supergiant's enormous envelope, are launched outward by the shock wave at thousands of kilometers per second. These layers are not uniform. Different layers correspond to different nuclear burning shells, each with its own composition, reflecting the specific nuclear reactions that produced it. The outermost layers, least altered from the star's original composition, are mostly hydrogen and helium. Deeper in, the layers become progressively enriched in the products of successive nuclear burning stages: carbon and oxygen from helium burning, neon and magnesium from carbon burning, silicon, phosphorus, and sulfur from neon and oxygen burning, and ion group elements from silicon burning closest to the core. When the shock wave from the core collapse passes through these layered shells, additional nuclear reactions occur. The shock heats the material briefly and intensely enough to trigger explosive nucleosynthesis, producing additional elements not synthesized in the star's normal burning stages. Nickel 5-6, a radioactive isotope of nickel, is produced in large quantities by this explosive nucleosynthesis, and its subsequent radioactive decay first to cobalt 5-6, then to iron 5-6, with characteristic timescales of days and months respectively, powers the optical light curve of the supernova for weeks to months after the initial explosion. The nickel 5-6 radioactive decay chain is the fuel that keeps a supernova shining long after the initial explosive energy has been radiated away, and measuring the light curve decay rate of a supernova provides a way to estimate how much nickel 5-6 was produced in the explosion. The expanding shell of supernova ejecta, the stellar material launched outward by the explosion, travels outward at its initial thousands of kilometers per second, expanding and cooling and thinning as it goes. Over years to decades, it sweeps up the circumstellar material that the star shed in its final stages of evolution, the material that Betelgeuse has been shedding through its stellar wind for millions of years, and that was added to in large quantity by the 2019 surface mass ejection. The interaction between the fast-moving supernova ejecta and the slower-moving circumstellar material produces a complex, multi-layered shock structure, an inner shock wave propagating outward through the circumstellar material, and a reverse shock propagating back inward into the ejecta that generates X-ray and radio emission observable from Earth for years to decades. This is exactly what has been observed in SN 1987A, where the expanding ejecta have been lighting up pre-existing rings of circumstellar material shed by the progenitor star in earlier evolutionary stages. For Betelgeuse, with its more complex and better-mapped circumstellar environment, including the material from the 2019 surface mass ejection, this interaction will be particularly rich and informative. The known structure of the circumstellar environment around Betelgeuse, established by current monitoring programs, will allow researchers to interpret the supernova circumstellar interaction in far more detail than was possible for 1987A, where the circumstellar environment was not as well characterized before the explosion. Over centuries and millennia, the supernova remnant, the expanding shell of stellar material, heated and illuminated by the ongoing interaction with circumstellar material and by the eventual spin-down radiation of the neutron star within, if one forms, becomes a diffuse, glowing nebula. The Crab Nebula is the remnant of the 1054 CE supernova, and at approximately 970 years old, it already stretches roughly 10 light-years across, visible as a patchwork of filaments and glowing gas through even a small telescope. A Betelgeuse supernova remnant, forming at a distance 7 times closer than the Crab Nebula, would be a spectacular object in the sky for millennia, eventually covering a significant portion of the constellation Orion as it expanded. The hunter's shoulder replaced by a glowing cloud of elements forged in the dying star. The neutron star that might be left at the center if Betelgeuse's mass is toward the lower end of its range, and a neutron star, rather than black hole forms, would likely be born spinning rapidly, converting the angular momentum of the collapsing core, originally the slowly rotating, enormous outer core of the red supergiant, but concentrated into a sphere 10 kilometers across, into a rotation rate of potentially hundreds of revolutions per second. Pulsars, the radio-emitting, rapidly rotating neutron stars that are regularly discovered in radio surveys, are often found at the centers of supernova remnants. The Crab pulsar, the neutron star at the center of the Crab Nebula, rotates approximately 30 times per second and has been slowing gradually over the nearly 1,000 years since the supernova that created it. A Betelgeuse pulsar, if one forms, would be the nearest pulsar to Earth by a wide margin, a laboratory for neutron star physics and dense matter physics at unprecedented proximity. The emotional register that Betelgeuse occupies in the popular imagination is worth examining, because it says something about how humans relate to astronomical objects and to the concepts of time and scale that astronomy forces on us. Betelgeuse is unusual among stars in having an established cultural presence that extends beyond professional astronomy. Its name is known far beyond the scientific community, partly because of its distinctive sound and partly because it was immortalized in popular culture. The 1988 film Betelgeuse, with its title based on a deliberate misspelling of the star's name, introduced the word into a generation's vocabulary through an entirely different context. The star's red color makes it visually memorable. Its position in Orion, one of the most universally recognized constellation patterns, gives it a familiar home, and its status as a candidate future supernova has given it a narrative drama that few other astronomical objects can claim. A star not just observed but anticipated, a celestial event horizon pointing toward a moment of spectacular change. There is something unusual about knowing that a specific visible star is going to explode. Most stars, including most of the ones visible in the night sky, are stable enough on human timescales that their eventual fates feel abstract and remote, intellectually known, but emotionally distant, like knowing that the sun will eventually become a red giant and consume the Earth in about 5 billion years. That is a fact with no particular emotional urgency. But Betelgeuse, in the same way that an elderly redwood tree or an aging volcanic edifice generates a different kind of attention than something in the middle of its life, commands a different quality of attention because its eventual dramatic end is nearer in cosmic terms. Nearer in cosmic terms is doing enormous work in that sentence, and the tension between nearer in cosmic terms and still almost certainly tens of thousands of years away by human measure is itself an interesting feature of the human experience of astronomy. We can know both things simultaneously, that Betelgeuse's explosion is imminent on stellar timescales and essentially irrelevant on human timescales, and yet the fact that it's the nearest such candidate, the one we can see directly with our eyes, the one we've given a name and observed for thousands of years, gives it an emotional reality that more distant supernova candidates lack. This emotional reality affects how the scientific work around Betelgeuse is covered and perceived. When the Great Dimming happened, the public response was immediate and intense in a way that a comparable anomaly in a distant, unnamed star would not have been. People who had never given a second thought to stellar evolution were suddenly asking whether Betelgeuse was about to explode. The hashtag circulated. The explainer articles multiplied. The scientific papers became, briefly, the subject of genuine popular discussion. And while some of that was sensationalism, some of it was something more valuable, a genuine moment of public engagement with a scientific story that happens to matter, where the drama of what was occurring in that distant star, transmitted through the light arriving at human eyes and through the professional alarm of the research community, actually reached and engaged a non-specialist audience. The scientists studying Betelgeuse generally understand this public dimension of their work, even when they're frustrated by simplistic reporting or by the expectation that they should be able to say definitively whether the star is about to explode. The public attention brings resources increased, telescope time, media coverage that influences funding decisions, popular support for astronomical observation programs that might otherwise be harder to justify to non-scientist stakeholders. And the public's genuine fascination with the star isn't irrational. A nearby red supergiant approaching the end of its life, doing something unprecedented with its surface, watched by every telescope that can be pointed at it, potentially the subject of the most spectacular astronomical event in human history that genuinely is interesting, not as a media construction, but as a physical reality. In thinking about what the ongoing monitoring of Betelgeuse represents in the history of scientific observation, it's worth appreciating how much the infrastructure of modern astronomy, the global network of observatories, the space-based telescopes, the alert systems, the data-sharing protocols changes what it's possible to know about a star like this. For most of human history, astronomical observation was limited to what could be seen with the naked eye, and later with telescopes of increasing but still limited power. The brightness of a star could be compared against reference stars and estimated to within perhaps half a magnitude on a good night. The color could be assessed qualitatively. The position in the sky could be measured with increasing precision over time, but the ability to actually see the surface of a star, to resolve its disk, to map its brightness distribution, to track the motion of features on its face was simply beyond reach for any star other than the Sun, and remained so until the second half of the 20th century. The very large interferometer technologies that allow modern observatories like ESO's VLTI to resolve the surface of Betelgeuse represent a genuine leap in what is observationally possible, not a small incremental improvement, but a qualitative change in the kind of information that can be extracted from the light arriving from distant stars. Similarly, the development of space-based observatories like Hubble, which can observe in ultraviolet and near-infrared wavelengths inaccessible from the ground, fundamentally expanded the available information about objects like Betelgeuse. The neutrino detectors that exist specifically to catch the burst from a nearby supernova represent yet another qualitative addition to the observational toolkit. The combination of all these different observational approaches, each sensitive to different physical processes, each revealing a different layer of the star's behavior, is what makes modern Betelgeuse monitoring qualitatively different from anything that was possible even 30 years ago. The 1987A observation was enormously valuable, precisely because multiple independent instruments happened to be running and happened to be capturing data. For Betelgeuse, the equivalent is not a matter of chance, it's a matter of deliberate coordination, of having built the infrastructure in advance and having the alert systems in place to respond. The scientific community has, in a real sense, learned from 1987A and done its best to prepare for the next equivalent event. This preparation itself represents a significant collective investment. Telescope time is scarce and expensive. Space observatory time is even more so. Maintaining monitoring programs over years and decades requires sustained funding, sustained institutional commitment, and sustained scientific interest, none of which are guaranteed in the face of competing scientific priorities and funding pressures. The fact that Betelgeuse monitoring has maintained and expanded its scope since the Great Dimming, rather than contracting as the immediate crisis faded from public view, reflects a genuine scientific consensus that the star's ongoing unusual state justifies continued intensive observation. The literature on Betelgeuse's eventual supernova has, over the years, generated some remarkable quantitative estimates of what that event would mean observationally. Thinking through these estimates is worth doing carefully, because they make concrete what would otherwise be abstract. At peak brightness, a Betelgeuse supernova is estimated to reach an apparent visual magnitude of somewhere between -7 and -12. The exact value depends on the luminosity of the explosion, which is uncertain, but these values bracket a reasonable range given what is known about core collapse supernovae from similar progenitors. For context, the full moon has an apparent magnitude of approximately -12.7. Venus, at its brightest, reaches about -4.9. Jupiter, at its brightest, is about -2.9. Sirius, the brightest star in the night sky, is magnitude -1.46. A Betelgeuse supernova at the upper end of the estimated range around magnitude -12 would be comparable to the full moon in total brightness, concentrated into a point source rather than an extended disk. The difference in experience between seeing a magnitude -12 extended object, the moon, and a magnitude -12 point source, the supernova, is qualitatively important. A point source of that brightness would appear almost unbearably intense to direct vision, far more dazzling than the moon, despite the equivalent total brightness, because all the light would be concentrated in an apparent zero size point rather than spread across the moon's roughly half-degree diameter in the sky. During daylight hours, it would be visible as a brilliant pinpoint in the blue sky, the way Venus is sometimes visible in daylight, but far more obvious. At night, it would dominate the sky in a way that nothing other than the moon currently does, casting sharp, hard shadows and making the stars near it in Orion difficult to see against the glare. The duration of visibility would depend on the evolution of the supernova's light curve, the characteristic brightening and fading over time that is driven by the radioactive decay of nickel 56 inches, the expanding ejector. Based on observed supernovae of the relevant type, the peak brightness phase would last days to weeks, followed by a gradual decline over months. After several months, the object would fade to the brightness range of a naked-eye star, then below naked-eye visibility as the expanding shell cooled and the radioactive decay powering its luminosity diminished. But for weeks around its peak, the event would be visible in daylight and dominant at night, and its presence in the sky would be noticed by every person on Earth who stepped outside. The scientific observations during those first weeks would be intense beyond any previous astronomical event. Every major observatory on Earth, Mauna Kea, La Palma, Cerro Paranal, the Atacama Desert, the South Pole, observatories across Asia, Europe, Australia, and the Americas would be dedicating their most capable instruments to Betelgeuse. Every space telescope with any capability to observe the relevant wavelengths would be pointed at Orion. The data rate would be enormous. The coordination challenges would be significant. But the preparation, the alert systems, the pre-planned observation strategies, the coordinated response protocols developed precisely for this possibility would, if functioning as designed, allow the scientific community to capture the event in unprecedented completeness from its very first seconds. The history of how humans have interpreted the appearance and disappearance of guest stars, supernovae, in modern understanding in historical records is itself a fascinating field bridging astronomy, history, and archaeology. The Chinese astronomical tradition maintained meticulous records of celestial events over more than 2 millennia, recording appearances of comets, novae, and supernovae, with sufficient precision that modern researchers can use these historical records to identify and date supernova remnants still visible today. The 1054 CE supernova that produced the Crab Nebula was recorded in the Song Dynasty Astronomical Chronicles as a guest star, appearing in what was described as the constellation we'd recognize as Taurus, visible in daylight for approximately 23 days, and visible at night for almost 2 years before fading. The Crab Nebula, still expanding and glowing nearly 1,000 years later, was definitively identified as the remnant of this event by matching the historical position with the modern location of the nebula. No European record of the 1054 event has been definitively identified, possibly because of the prevailing Aristotelian orthodoxy that held the heavens to be unchanging. A new star would have been deeply theologically troubling, and monks who observed it might have been reluctant to record it. Japanese and Korean astronomical records also captured the 1054 event, adding further confirmation. Native American rock art at several sites in the American Southwest has been interpreted as depicting the 1054 supernova alongside a crescent moon, with the relative position and timing consistent with the historical astronomical record, though the interpretation is debated. If accurate, these petroglyphs would represent the only known artistic depictions of a supernova event made by its contemporary observers. The 1006 CE supernova, sometimes called the brightest supernova in recorded history, was captured in astronomical records from China, Japan, the Islamic world, and medieval Europe, and was visible for years, reaching a peak estimated at somewhere between magnitude -7 and -9, similar to what is expected for a Betelgeuse supernova. European chronicles describe a new star in the southern sky that was so bright it cast shadows. Islamic astronomers in Egypt provided detailed positional records that allowed 20th century astronomers to identify the remnant of this 1006 CE event, a supernova remnant now designated SN 1006 inches Lupus, approximately 7,200 light-years from Earth. If the 1006 supernova at 7,200 light-years was bright enough to cast shadows, a Betelgeuse supernova at 700 light-years 10 times closer, therefore more than 100 times brighter by the inverse square law, would be something on a different scale of observational experience entirely. These historical records matter for more than purely historical interest. They provide data points on supernovae that would otherwise be entirely unknown to modern astronomy, And the associated remnants, the expanding shells of stellar material now detectable in radio and X-ray observations, allow researchers to study the long-term evolution of supernova remnants at known ages. The Crab Nebula's age is known precisely because the 1054 CE record gives the year of the explosion. The SN 1006 remnant's age is similarly constrained by the historical record. In each case, the combination of a historical observation and a modern remnant provides a constraint on supernova physics, how remnants evolve over time, how the central compact object pulsar, or lack thereof, behaves that could not be obtained by studying remnants of unknown age. A Betelgeuse supernova in the modern era would be the first galactic supernova to occur after the development of systematic global astronomical monitoring with photographic and digital records, high-resolution spectroscopy, space-based observatories, neutrino detectors, and gravitational wave instruments. Every previous galactic supernova in history was observed with whatever technology existed at the time of the event. The naked eye in 1054 and 1006, Tycho's careful positional measurements in 1572, Kepler's photometric assessments in 1604. A modern galactic supernova would be the first of its kind in the age of truly capable astronomical instrumentation, and Betelgeuse, as the nearest candidate, is the most likely source. Let's bring all of this back to where it started, to that red-orange point of light in Orion's shoulder, to the act of looking up on a clear winter night and knowing what you're actually seeing. The scientific community's sustained, intensified attention to Betelgeuse is not irrational, not sensationalist, not the product of misguided alarm. It's the product of three things converging in one place: a star genuinely capable of the most spectacular event in the history of human astronomy, a recent series of events that demonstrated the star is more behaviorally complex and more capable of surprise than models had predicted, and an awareness that the preparation done now will determine how scientifically rich the event is when it eventually occurs, regardless of whether eventually means 500 years from now or 50,000. The monitoring programs continue. The papers accumulate. The neutrino detection networks stay online. The interferometric surface images are taken when weather and scheduling allow. The photometric brightness records extend by another data point every clear night, fed in by professional observatories and by amateur astronomers with backyard telescopes who understand what they're contributing to. The theoretical models are revised and refined, incorporating the lessons of the Great Dimming and the subsequent brightness surge. The next generation of researchers learns the star's history, takes up the monitoring responsibilities from those who came before, and continues the observation. This is science on a timescale that humbles any individual contribution. No single paper solves the problem of Betelgeuse. No single observation settles the question of when it will explode. The work is collective, cumulative, multi-generational, a relay race where the baton is a monitoring program and the finish line is an event that will occur on a schedule entirely indifferent to human planning. The people running the relay today will not see the finish line. Their successors might or might not. But the baton will be passed, the monitoring will continue. And when the moment comes when the neutrinos arrive and the sky over Orion catches fire in the most spectacular light show in human history, the scientific community will be ready, because the people who came before them did the work to make that readiness possible. Go outside tonight and look for it. The red-orange point in the shoulder of Orion. The light arriving at your eyes from 700 years ago, from a star that is older than human civilization, larger than anything in our solar system, burning with the energy of 100,000 suns, gradually and inevitably approaching its extraordinary end. The people watching it through their instruments tonight are doing something rare in science, preparing for an event they believe in completely, have calculated carefully, and may never personally witness. They are building readiness for a future they can't see, on behalf of a scientific community that doesn't yet exist, for an astronomical event whose exact timing they cannot predict. That patience, that sustained collective attention across generations, that willingness to build for a future whose schedule is entirely set by physics and not by human preference, that is what the Betelgeuse monitoring enterprise actually is. And Betelgeuse, burning in the winter sky, enormous and red-orange, and gradually dying in the most spectacular way a star can die, has been waiting 8 million years for the moment it will finally be seen. By whoever is watching when it happens, they will have those who watched it tonight and every night for generations to thank for the instruments pointed in exactly the right direction, at exactly the right moment, to capture everything. The physics of what astronomers call stellar death is worth unpacking at a level of detail that most general descriptions skip, because the specifics are where the genuine strangeness lives, and Betelgeuse's situation connects to each of those specifics in a way that makes the abstract concrete. When Betelgeuse's core eventually fails and collapses, the sequence that follows involves physical conditions that have no analogue anywhere in ordinary human experience, and that remains some of the least well understood in all of physics. The collapsing core reaches densities at which the normal rules governing matter, the quantum mechanical principles that keep electrons in their shells, that keep atoms from overlapping, that prevent any two fermions from occupying the same quantum state, are pushed to their limits and beyond. At nuclear density, the density of atomic nuclei themselves, approximately 200 trillion kilograms per cubic centimeter, matter behaves in ways that cannot be tested in any laboratory on Earth. The only places in the universe where these conditions occur naturally are in the moments of stellar core collapse and in the neutron stars that sometimes result. The equation of state of matter at these extreme densities, the mathematical description of how pressure, density, and temperature relate to each other in dense nuclear matter, is one of the outstanding unsolved problems of theoretical physics. Multiple competing models exist, with different assumptions about how nuclear forces behave when neutrons and protons are packed together at nuclear density, and these different models predict different properties for the resulting neutron stars, different maximum masses, different radii, different internal structures. Observational constraints on the equation of state come from measurements of neutron star masses and radii, from gravitational wave observations of neutron star mergers, and from the neutrino emission profiles of the handful of supernovae that have been observed. A Betelgeuse supernova, with its wealth of neutrino data, would provide the strongest observational constraint on the equation of state of dense nuclear matter in history, a pure physics payoff from an astronomical event. The question of whether Betelgeuse forms a neutron star or a black hole is itself related to this physics. The maximum mass that a neutron star can support against gravity, the Tolman-Oppenheimer-Volkoff limit, depends on the equation of state. If nuclear matter is stiffer than current models suggest, higher maximum neutron star masses are possible, and a wider range of collapsing cores will produce neutron stars rather than black holes. If nuclear matter is softer, the maximum mass is lower, and more collapses will produce black holes. Measuring the neutrino emission from a Betelgeuse core collapse would constrain which scenario actually occurred, and by extension would constrain the equation of state of dense nuclear matter in a way that no other observation currently can. The formation of a black hole in a stellar collapse is its own remarkable physical event. As the core collapses beyond the neutron star density, if the remaining mass is too large to be supported even by neutron degeneracy pressure, the collapse continues. Within fractions of a second, the core shrinks to a radius smaller than its Schwarzschild radius, the critical radius below, which not even light can escape, and a black hole forms. The event horizon, the surface of no return, expands outward at the speed of light through the infalling material. From the perspective of any observer outside the forming black hole, the collapse appears to slow and freeze asymptotically at the event horizon due to gravitational time dilation. From the perspective of the infalling material itself, the collapse continues in finite proper time until the singularity at the center. A black hole formed in this way would cut off the neutrino emission abruptly, providing a clean observational signature distinguishable from the slower, sustained neutrino cooling of a neutron star. If Betelgeuse forms a black hole directly, the neutrino burst from the initial collapse would be followed by an abrupt cutoff, the detector signal going from intense to zero in milliseconds, as the event horizon formed and swallowed the neutrino-emitting surface. That abrupt cutoff, if observed, would be the first direct observational evidence of black hole formation in real time. Not inferred, not modeled, not deduced from the absence of a pulsar in a centuries-old remnant, but directly observed, the neutrino signal simply stopping as the event horizon formed and consumed the collapsing core. The few milliseconds between the last neutrino and the silence would be the most scientifically dense moment in the history of astrophysics. The scale of the scientific return from a well-observed nearby supernova is difficult to overstate, and it's worth being specific about the different physics questions it would address simultaneously, because each one represents a frontier problem in its own right. The equation of state of dense nuclear matter, already discussed, is one. The mechanism of core collapse supernova explosions is another. Despite decades of theoretical work and increasingly sophisticated computer simulations, astrophysicists do not yet have a fully satisfactory understanding of how the shock wave generated by the core bounce manages to escape outward through the star rather than stalling and falling back inward. The shock wave, as it propagates outward through the infalling stellar material, loses energy to neutrino heating and to the dissociation of heavy atomic nuclei processes that drain energy from the shock and threaten to stall it. In most simulations of spherically symmetric collapses, the shock stalls, something revives it. The leading candidate is neutrino-driven convection. The intense neutrino flux from the cooling proto-neutron star heats the material just behind the stalled shock, creating convective instabilities that eventually provide enough energy to reinvigorate the shock and allow it to escape. But the details of this process, the exact mechanism, the role of rotation and magnetic fields in the collapsing core, the three-dimensional structure of the convective flows remain actively debated, and different simulation codes incorporating different physics assumptions give different answers. A Betelgeuse supernova, observed from its very onset with both neutrino detectors and optical telescopes, would provide direct constraints on the shock revival mechanism. The timing of the optical brightening relative to the neutrino burst the delay between the neutrino emission from the core and the first optical signal from the shock breaking through the photosphere carries information about how the shock propagated through the star's layers. The energy and spectrum of the neutrinos carry information about the conditions at the proto-neutron star surface where the neutrino emission is generated. Comparing all of this to the predictions of different simulation models would test those models in a way that no indirect evidence or observational constraint from previous, more distant supernovae can match. The role of rotation in the collapse is another open question. If the collapsing core is rotating rapidly, rotating fast enough that the angular momentum concentrated into the small radius of the nascent neutron star produces a millisecond pulsar, the dynamics of the collapse and explosion are qualitatively different from the spherically symmetric case. Rapidly rotating collapses are predicted to produce stronger gravitational wave signals, more asymmetric neutrino emission, and potentially the formation of magnetars neutron stars with extraordinarily intense magnetic fields that can power unusually energetic supernovae. Whether Betelgeuse's core is rotating rapidly enough to produce these effects is unknown. The star's surface rotation is measured to be slow, but the core's rotation rate could be significantly different due to differential rotation during the evolutionary process. The gravitational wave signal, if detected, would directly constrain the rotation of the collapsing core. The composition of the ejected material, which elements are produced in what quantities by the explosion, how they are distributed in the expanding ejector, is a third frontier question. Nucleosynthesis in core collapse supernovae is understood in broad outline, but poorly constrained in detail. The production of elements from oxygen through iron in the supernova explosion the alpha elements, like magnesium, silicon, calcium, and titanium, that are the primary products of massive star nucleosynthesis, plus iron group elements from the innermost layers of the explosion, depends sensitively on the detailed physics of the explosion, the temperature and density profiles of the expanding ejector, and the properties of the nuclear reactions occurring during the shock heating. Spectroscopic observations of the expanding supernova atmosphere, tracking the appearance and evolution of specific elemental signatures over weeks and months, would constrain these nucleosynthesis models in unprecedented detail. The dust that forms in the supernova remnant as the expanding, cooling ejector condenses into solid particles is another area of active research. Supernovae are known to be significant sources of cosmic dust, the fine solid particles that pervade interstellar space and that play crucial roles in star and planet formation. The dust formed in the expanding ejecta of recent supernovae, including SN 1987A, has been directly detected and characterized in infrared and radio observations. A Betelgeuse supernova remnant, forming at close range, would allow the study of supernova dust formation in more detail than any previous event tracking the condensation of specific dust species, the evolution of their properties as the remnant ages, and the interaction of the dust with the surrounding interstellar medium. All of these questions, the equation of state, the explosion mechanism, the nucleosynthesis, the dust formation, the neutron star or black hole formation, are currently addressed through observations of distant supernovae and supernova remnants, where the limited signal-to-noise and spatial resolution of the observations constrain what can be learned. A Betelgeuse supernova, at 100 times the distance of the nearest galaxy-hosted supernovae, would unlock precision measurements across all of these questions simultaneously. The scientific literature generated by that single event would reshape our understanding of stellar physics in a way that no gradual accumulation of data from distant events can match. Understanding where Betelgeuse fits in the full landscape of stellar types, masses, and evolutionary stages helps clarify why it's both representative of an important class and unique in its accessibility. Stars form with a range of initial masses, from the smallest red dwarfs at about 1/10 the mass of the Sun, up to the largest known stars at perhaps 200 or more solar masses. This mass spectrum is not uniform. Lower mass stars are far more common than higher mass stars, a relationship captured in what's called the initial mass function. For every star massive enough to end as a core collapse supernova, roughly 8 or more solar masses, there are dozens or hundreds of less massive stars that will end their lives as white dwarfs. This is why supernovae, while individually spectacular, are relatively rare on the scale of the whole galaxy. The red supergiant phase is characteristic of massive stars in a specific range of masses, roughly 8 to 35 solar masses, depending on the star's initial composition and rotation. Stars at the lower end of this range spend a long time as red supergiants before eventually collapsing. Stars at the upper end of the range may evolve through the red supergiant phase relatively quickly, and then lose enough mass through strong stellar winds to evolve back toward hotter surface temperatures, becoming luminous blue variables, Wolf-Rayet stars, or other evolved massive star types before their final collapse. The evolutionary tracks in this mass range are complex and depend sensitively on parameters initial composition, rotation, mass loss rates that are not always well constrained for any individual star. Betelgeuse, at 10 to 20 solar masses, sits in the middle of the red supergiant range, firmly expected to end its life in a core collapse supernova, rather than evolving back toward hotter surface temperatures or collapsing prematurely. Its evolutionary track, while uncertain in detail, is broadly predictable. Continue as a red supergiant, continue losing mass through stellar winds, and possibly through additional SME events, eventually exhausting the nuclear fuel in successive burning stages, and ultimately undergo core collapse and explode. The uncertainty in Betelgeuse mass, the span from 10 to 20 solar masses, matters most for the specific characteristics of the supernova it will produce. More massive progenitors tend to produce more energetic supernovae, with more nickel, 5, 6, and a brighter, longer-lasting light curve. They also produce more massive remnants. A 2-0 solar mass core is more likely to collapse directly to a black hole, while a 1-0 solar mass core is more likely to produce a stable neutron star. Observationally constraining the mass of Betelgeuse better than the current factor of 2 uncertainty would be enormously valuable for predicting the characteristics of the eventual supernova, but the measurement is limited by the same distance uncertainty and model uncertainties that plague all of the star's derived physical properties. The comparison of Betelgeuse with other well-studied red supergiant stars like Antares, RSG Puppis, W Persei, S Persei, and others in the Milky Way is instructive. Each of these stars has its own variability characteristics, its own mass loss behavior, its own circumstellar environment. Together, they form a sample that allows stellar evolution theorists to test models of red supergiant behavior against real observations. Betelgeuse stands out from this sample primarily by virtue of its proximity. Its closeness to Earth allows a level of observational detail that simply isn't achievable for the others, but the physical processes operating in Betelgeuse are the same ones operating in all of them. As understanding of Betelgeuse deepens through continued observation, the insights propagate outward to the broader population of red supergiants, improving understanding of an entire stellar class rather than just one exceptional nearby member. One final dimension of the Betelgeuse story deserves extended attention. The question of what the star's current unusual behavior might imply about the standard framework of stellar evolution that astrophysicists have built over the last century, and whether that framework needs revision in ways that go beyond simply adding surface mass ejection physics to the models. Stellar evolution theory is one of the great achievements of 20th century astrophysics. Starting from the basic physics of nuclear reactions, radiation, transport, and gravity, it was able to account for the observed properties of stars across the full range of masses and evolutionary stages, to predict the existence of stellar objects before they were observationally confirmed, and to explain the distribution of stellar types in the galaxy in terms of an evolving population born, living, and dying according to predictable physical rules. The Hertzsprung-Russell diagram, the fundamental tool for classifying stars by their luminosity and temperature, became an evolutionary map as well as an observational catalogue, with different regions corresponding to different phases of stellar life, and the paths connecting them corresponding to evolutionary tracks that stars follow as they age. Betelgeuse, as a red supergiant, occupies a well-defined region of this diagram. Its position high luminosity, low surface temperature, is consistent with an evolved massive star in the late stages of its nuclear burning. The models predict that stars of this type should be variable, should be losing mass, should have extended circumstellar envelopes. All of this is observed. The models did not predict the 2019 surface mass ejection, but that's partly because SMEs of this type had never been observed before and therefore weren't included in the models. Not necessarily because the models are fundamentally wrong, but because they were built on an incomplete observational basis. The more interesting question is whether the Great Dimming and subsequent events suggest that Betelgeuse is in a different evolutionary stage from what the standard models predict for a star of its properties. Some researchers have argued that the star's unusual behavior might indicate it has advanced further through its nuclear burning stages than its surface properties, suggest that the interior might be in a more advanced state, burning carbon, neon, or oxygen, rather than the helium that a star of Betelgeuse's surface properties might be expected to be burning. If true, this would mean the star is closer to its final core collapse than standard models would predict, and would offer a partial explanation for the unusual variability. Advanced nuclear burning stages produce more energy per unit time, which can drive more vigorous convection and larger-scale surface events. This interpretation remains speculative and controversial within the research community. Others argue that the surface mass ejection and subsequent disruption of the pulsation cycles can be fully explained without invoking an unusual or advanced evolutionary state, that the star simply had a large convective upwelling which happens stochastically in red supergiants, and that the consequences played out exactly as the physics predicts, without requiring any special evolutionary status. The difficulty of distinguishing between these interpretations is fundamental. The core, where the relevant nuclear burning is occurring, is inaccessible to direct observation. Surface behavior can be influenced by many factors that don't directly reflect the evolutionary stage, and the turbulent, dynamic outer layers of a red supergiant can produce unusual events through purely surface-level physics without any change in the core. Resolving this ambiguity, determining whether Betelgeuse's unusual behavior is a symptom of advanced evolutionary state or simply a demonstration of the range of stochastic surface behavior possible in red supergiants, is one of the central goals of ongoing research. It requires better models of red supergiant convection, better observational constraints on the star's internal structure to the extent possible from surface observations, and continued monitoring to determine whether the unusual behavior is a one-time disruption that the star is settling out of, or an ongoing pattern that might reflect a persistently different internal state. The implications of these two interpretations are very different. If the unusual behavior is purely surface-level stochasticity, then Betelgeuse is a well-behaved red supergiant that happened to have a dramatic convective event, and the star is on the normal evolutionary timeline for its mass and age many thousands of years from core collapse at minimum. If the unusual behavior reflects advanced evolutionary state, then the timeline might be significantly shorter, and the star's variability in coming years and decades might show patterns consistent with the more intense internal energy generation of the late nuclear burning stages. The monitoring programs, maintained consistently over the coming decades, might eventually accumulate enough data to distinguish between these possibilities if the star's behavior continues to be unusual in ways consistent with an advanced evolutionary state, or if it settles back into a more ordinary red supergiant variability pattern. This is, in miniature, the whole of what makes Betelgeuse so scientifically valuable and so professionally engaging for the researchers who study it. It's a system rich enough in observable behavior, close enough to study in detail, and uncertain enough in its current state that continued observation continues to be scientifically productive. Every new season of monitoring adds data that constrains models, challenges interpretations, and sometimes overturns them. The star continues to surprise, the community continues to adapt, and the conversation between observation and theory that is the core of empirical science continues, conducted against the backdrop of a star whose eventual supernova will be the punctuation mark at the end of one of astronomy's great extended sentences. Betelgeuse is in the sky tonight. The instruments are watching. The data is flowing into servers and into the hands of researchers on several continents. And somewhere out there, 700 light-years away, the star continues burning enormous, ancient, restless, surprising, carrying its secret of when it will finally, spectacularly, end. If you want a single image to carry away from everything in this story, something that captures both the science and the human dimension of what's happening with Betelgeuse right now, consider this one. Somewhere tonight, in a windowless room at a telescope facility, or in a university office lit by monitor glow, or in a basement laboratory dominated by a large tank of ultra-pure water instrumented with thousands of sensitive light detectors, there is a scientist who has set up an automated alert. It will ping their phone if Betelgeuse's brightness drops or surges beyond a threshold. It will trigger a cascade of notifications to collaborators, to observatories, to other monitoring networks, if the star starts doing something that the standard models say it shouldn't be doing. They set this alert not because they expect to receive it tonight, or next month, or next year. They set it because the cost of missing the first hours of a Betelgeuse supernova, the shock breakout, the initial neutrino burst, the very earliest optical signal, is too high to risk for lack of preparation. And so the alert sits there, armed, patient, waiting for a signal that might not come for 50,000 years or might come before this sentence is finished. That is the kind of attention Betelgeuse has earned. Not the frantic attention of something expected imminently, but the sustained, careful, professionally responsible attention of something whose eventual occurrence is certain and whose scientific value is so large that preparation is permanently justified regardless of the timeline. It's the attention you give to something important, not urgent, but important, in the way that a thing can be important on timescales larger than any individual human life without losing any of its significance. The red-orange star in Orion's shoulder has been burning for 8 million years, and it has, for the last several years, been doing something new, something unprecedented, something that the careful observers watching it did not predict and are still working to fully understand. And in this moment of particular scientific uncertainty, with the star's pulsation cycles disrupted and its surface behavior unusual and its evolutionary stage genuinely uncertain, the most honest summary is this: we are watching something remarkable happening to a remarkable object, and we do not know exactly what comes next, but we know it will be worth watching. It has always been worth watching. That is why we named it, why we measured it, why we built instruments capable of seeing its face, why we keep the alerts armed, and the telescopes pointed, and the monitoring programs running through every season and every year that passes. Betelgeuse is not done surprising us. Of that much, we can be reasonably confident. There is one more thing worth saying before closing this story, and it concerns the nature of scientific patience itself, the particular kind of intellectual endurance that astronomical science demands, and that the Betelgeuse case exemplifies in an unusually pure form. Most sciences operate on timescales where a researcher can reasonably expect to see the results of their work within a career. A biologist studying a disease can expect to see treatments developed, tested, and deployed. A chemist synthesizing a compound can see the results of a reaction in hours. Even most astronomers spend their careers studying objects whose changes are observable within human timescales: the evolution of a galaxy, the formation of a star, the dynamics of a stellar cluster. These processes take millions of years in absolute terms, but the changes visible from year to year or decade to decade are real and measurable and constitute a form of progress that a scientist can witness personally. Betelgeuse is different. The researchers maintaining monitoring programs for this star are doing work whose ultimate payoff, a complete, well-observed record of a nearby stellar supernova, may not materialize for many lifetimes. The careful brightness measurements taken tonight will contribute to a dataset whose most important moment of use may come centuries from now. When a scientist in a situation and a world we cannot currently imagine opens the historical archive and finds, at the precise moment before the first neutrino signal arrived at Earth, the last normal data point from a star that was about to change the sky, that future scientist will not know the names of the people who took tonight's measurement. They may not know the institution or even the country where the telescope was operating. They will know only the data, the precise brightness, the carefully calibrated wavelengths, the timestamps accurate to fractions of a second, and they will use that data in the analysis of the most important astronomical event their generation has ever witnessed. And the data will be there, reliable and complete, because generations of researchers before them treated the work as worth doing, even in the full knowledge that they themselves would never see it reach its most meaningful moment. This is what scientific legacy actually looks like, stripped of the more legible forms of recognition and accomplishment. Not a discovery that bears your name, not a treatment that saves lives in your lifetime, not a technology that transforms the world while you are still present to see it. Just data, carefully taken, carefully stored, waiting for a moment that will come when it will come, contributing its irreplaceable fraction to an understanding that no single generation can complete alone. The red star burns on, the instruments watch, the data accumulates, and somewhere in the archive, tonight's measurement waits for the future scientist who will need it. That is Betelgeuse, And that, in the end, is why it matters. The sky is waiting, so are we. And every winter night, between now and that moment, whenever it comes, offers the same invitation. Step outside, find Orion, look for the reddish-orange point blazing in the shoulder position, and know that you are looking at one of the universe's great unfinished sentences, still burning, still surprising, still being watched. Still watched by people who understand what they're seeing, and grateful for the few thousand years of light still left to witness before it writes its final, blazing word.